The universe is vast, dark, and, for the most part, utterly silent. When we look up at the night sky, we see a blanket of twinkling lights, a comforting canopy that has inspired poets and dreamers for millennia. But that comfort is a lie, or at least a very convenient illusion. The reality of deep space is a theater of extremes so violent, so alien, and so utterly hostile that our home planet, with its gentle rains, breathable air, and stable sun, begins to feel like a miraculous anomaly. We are about to embark on a journey to 6 of the most terrifying worlds ever discovered by human science. But before we go, we need to define what horrifying means in a cosmic context. To us, horror on Earth is a monster under the bed, a sudden noise in the dark, or a natural disaster. In space, horror is different. It is the absolute and total rejection of life. It is a planet that rains molten rock. It is a world being torn apart by its own star, a slow, agonizing death that lasts for millions of years. It is the sheer crushing loneliness of a rogue planet drifting forever in the endless black, with no star to call home. Horror is also deception, a planet that never was, a ghost in the data that tricks the finest minds in astronomy. And yes, it is the profound silence of an ancient world that has existed for billions of years, a world that might have hosted life long before Earth even formed, only to leave us with no answer to the question, were we ever alone? To understand these places, we first need to understand how we even know they exist. Most exoplanets are not seen directly. They are far too small and dim compared to their parent stars. Instead, we find them through shadows and wobbles. The most common method is the transit method. Imagine a fly crawling across a massive searchlight. You wouldn't see the fly, but you would notice a tiny, regular dip in the light. That is how the Kepler Space Telescope and other observatories find planets. They stare at millions of stars, waiting for that telltale flicker of a shadow passing between the star and Earth. When we say a planet is relatively close, like 13 light-years away for Captain B, or 489 light-years for Corot 7b, we are using a scale that is almost impossible to grasp. A light-year is the distance light travels in 1 year, about 5.88 trillion miles. The closest star to our Sun, Proxima Centauri, is a little over 4 light-years away. So, 489 light-years is not close. It is an unimaginable gulf. But in the cosmic ocean, where the Milky Way galaxy is 100,000 light-years across, 489 light-years is practically a neighbor. It is a distance that allows us to study these worlds in detail, but a distance that ensures we will never, ever touch them. With that context, let us turn our eyes to the first horror on our list. Welcome to Corot 7b, a planet that makes hell look like a vacation resort. Corot 7b is a rocky world, about 1.5 times the size of Earth. It was discovered in 2009 by the French-led Corot mission, and it was a landmark discovery, the first confirmed rocky exoplanet. This should have been a triumph, but as scientists looked closer, they realized they had found something far more sinister. This planet orbits its star, Corot 7, which lies in the constellation Monoceros, the unicorn. Do not let the whimsical name fool you. This star is a killer. Corot 7b is 60 times closer to its star than Mercury is to our Sun. Stop and think about that for a moment. Mercury is already a scorched, airless rock where surface temperatures can reach 800 degrees Fahrenheit. Now, imagine being 60 times closer. The planet is tidally locked, meaning one side permanently faces the star, a hemisphere of eternal blazing day. The other side faces away, an eternal frozen night. On the day side, the temperature soars to 4,700 degrees Fahrenheit, 2,600 degrees Celsius. That is hot enough to melt rock, to vaporize metal. The surface of Corot 7b is not solid rock. It is a vast, roiling ocean of liquid lava, glowing with the heat of a star. But here is where the story becomes truly horrifying. The high heat creates a process of geological evaporation. Rock doesn't just melt, it boils. Vaporized minerals, including silicates and iron, rise into the thin, superheated atmosphere. They travel to the boundary between the day side and the night side, where the temperature plummets by thousands of degrees. Here, the vapor condenses. It turns back into solid particles, and then it falls. On Corot 7b, it rains rocks. Not water, not even sulfuric acid. Gravel. Tiny, sharp-edged fragments of stone falling from a black sky. Imagine standing there, on that razor-thin twilight zone at the edge of the lava ocean. On one side, a horizon of liquid fire. On the other, a frozen wasteland dark as a cave. And from above, a constant hissing drizzle of hot rock chips. There is no wind, no sound, but the sizzle of stone on stone. Astronomers believe Corot 7b was not always like this. It was likely a gas giant initially, a world the size of Jupiter, perhaps even larger. But as it spiraled closer to its star over billions of years, the immense radiation and stellar wind stripped away its gaseous envelope layer by layer, like peeling an onion. All that remains is the doomed, super-dense rocky core, a planet murdered by proximity, reduced to a cinder. This is not a place for life. It is a monument to destruction. But let us move from a world of fire to a world of ice and rings. If Corot 7b is a vision of hell, then J1407b is a vision of a cosmic cathedral of doom. J4407b is a gas giant, a massive planet between 10 and 40 times the mass of our own Jupiter. It lies about 434 light-years from Earth. At first glance, it looks familiar. It has rings, like Saturn. But here, the similarities end. Saturn's rings are beautiful, yes, but they are modest. They span about 175,000 miles in diameter. The rings of J4407b are a monstrosity. They are 200 times wider than Saturn's rings. They span over 110 million miles. To put that in perspective, that is more than the distance from the Earth to the Sun. If Saturn's rings were this size, they would fill a huge portion of our inner solar system, reaching past the orbit of Venus. This planet has 30 separate rings, each one a disk of rock and ice debris, and each one with its own orbital dynamics. How do such rings form? The answer is violence. These are not the gentle leftovers of a moon that never formed. These are the graveyards of moons that were destroyed. The sheer gravity of J1407b, a beast of a planet, would have torn apart any satellite that ventured too close. The planet may have had a family of moons, large and small. One by one, they were ripped apart by tidal forces, ground into rubble, and spread into a vast disk. There is evidence of a massive gap in these rings, a gap that suggests a collision. A satellite with a mass somewhere between Earth and Mars likely smashed into the ring system or into another moon, leaving a trail of destruction. The rings themselves have a total mass roughly equal to Earth's. It is a system in chaos. Visualizations of J1407b are haunting. Imagine standing on a hypothetical moon that somehow survived this cataclysm. You look up. The sky is not blue. It is a deep starry black, because the planet is far from its star. But above you, arching from horizon to horizon, is a wall of debris. The rings are so wide and so thick that they block out the stars. They glint in the faint starlight, a band of silver and rust-colored dust. You see gaps where the rings have been cleared by strange shepherd moons, and you see waves and ripples in the material, echoes of ancient collisions. The planet itself looms overhead, banded and stormy, a giant lord over a kingdom of broken stone. This is not a place of tranquility. It is a place of ongoing, grinding catastrophe. And there is even a theory that J1407b might not be a planet at all. It might be a failed star, a protostar that never gathered enough mass to ignite nuclear fusion. It orbits its host star not like a planet, but like a close companion in a binary dance. If true, this object is neither star nor planet. It is a cosmic hybrid, a reminder that the universe does not always follow our neat categories. From a system of giant rings, we now travel to the loneliest planet in the known universe. Its name is PSO J318.522, and it is a rogue planet. Most planets live in the warmth of a star. They have a home. PSO J318.522 has none. It drifts alone in the void, about 80 light-years from Earth. It is a gas giant, about 8 times the mass of Jupiter, but it has no sun to orbit. It was likely born in a planetary system, but through gravitational interactions with other planets, or perhaps the influence of a passing star, it was ejected, thrown out, exiled. It is now a wanderer, forever falling through the interstellar medium. For astronomers, this rogue planet is a gift. Because it is not washed out by the blinding light of a parent star, they can study it directly. They have observed its infrared glow. The planet is young, only about 12 million years old. Its surface is still hot from its formation, a scorching 1,470 degrees Fahrenheit. It rotates rapidly, completing one full spin every 5 hours. Its clouds are exotic. They are made of dust and molten iron. The weather forecast on PSO J318.5-22 is a nightmare, cloudy with a chance of iron rain. The winds can reach several times the speed of sound. There are storms that rage across its surface, invisible to the eye, but detectable as shifts in brightness. But the real horror of this planet is not its weather. It is its context. Imagine being on this world. There is no sun. The sky is not black. It is completely, utterly absent of light. There is no day and night. There is only an eternal twilight, lit by the faint, distant glow of 1 trillion stars that are too far away to provide warmth. The planet is drifting. It is moving at a velocity of tens of thousands of miles per hour, but there is no reference point. You cannot feel motion in the void. It is the ultimate sensory deprivation. You are on a hot, storm-ridden world, trapped in an endless fall through nothingness. There is no destination. There is no hope of ever reaching another star. This planet is a ghost of a system, doomed to wander for billions of years until, perhaps, a star's gravity captures it again. Or, more likely, it will simply cool down, its inner fire fading, until it becomes a cold, dark sphere, an invisible tombstone drifting in the galactic graveyard. We have seen fire, we have seen rings of ruin, we have seen isolation. Now, we look at a planet that is actively dying right before our telescopes. WASP-P12b is a gas giant located about 1,400 light-years away. It is roughly twice the size of Jupiter, and it is being eaten alive. WASP-12b orbits its star with terrifying speed. 1 year on this planet lasts just over 1 Earth day. It is so close to its star that the star's gravity is tearing it apart. The planet is not a sphere. It is an egg-shaped, stretched ovoid. The outermost layers of its atmosphere are being siphoned off by the star, streaming away into space like blood from a wound. This is not a metaphor. It is a literal process of destruction. The planet is losing mass at a rate of about 10^7 Jupiter masses per year. That might sound small, but it is a steady hemorrhage. The planet is shedding its outer layers into a disk of material that spirals down onto the star. Hubble Space Telescope observations have detected a stream of matter flowing from the planet, a visible comet-like tail of gas. Even more startling, scientists have found evidence of water in this stream. Water boiling away into space on a planet that reaches temperatures of 4,100 degrees Fahrenheit. It is a paradox, and yet there is a darker, more wonderful twist to this story. The planet has an extremely high carbon-to-oxygen ratio. This suggests that the planet's interior, if it has a solid core, might be composed largely of graphite and diamond. That is right. Deep inside this dying, tortured world, there might be a planet-sized diamond. The media loved this, calling WASP-12b the Diamond Planet. But do not let the sparkle fool you. That diamond is a tomb. The planet is doomed. Computer models suggest that in the next 10 million years, WASP-12b will be completely torn apart. It will be consumed by its star, its matter scattered into the star's atmosphere, becoming one with the very fire that killed it. It is a slow, agonizing death, a celestial body being digested alive. This leads us to a planet that never was, a story of a scientific haunting. Meet Fomalhaut b, also called Dagon. In 2008, the Hubble Space Telescope captured a direct image of what looked like a planet orbiting the bright star Fomalhaut, located just 25 light-years away. It was a sensational moment. Fomalhaut is one of the brightest stars in our night sky, visible to the naked eye. It is surrounded by a massive cold debris disk of dust and gas. And there, right in the middle of the disk, was a small point of light. It was moving. It was clearly orbiting the star. It was named Fomalhaut b, after the star, and astronomers believed they had discovered a massive exoplanet, perhaps 3 times the mass of Jupiter. But as time went on, the object began to behave strangely. It moved faster than it should. Its brightness started to change. It appeared to be getting larger, but dimmer. And then, in 2014, it vanished. The planet was gone. Astronomers were baffled. They went back to the data. They re-examined the images, and they came to a radical conclusion. Fomalhaut b was never a planet. It was a ghost, a collision. Back in 2004, during a preliminary survey of the Fomalhaut system, 2 large bodies, perhaps asteroid or protoplanets, had smashed into each other. The collision created a massive cloud of dust and ice. This cloud was illuminated by the star and looked like a planet. Over the next few years, as the cloud expanded and dissipated, it grew larger and fainter, exactly as the data showed. By 2014, the cloud had dispersed enough that it was no longer visible. The planet was an illusion, a transient scar from a cosmic car crash. The story of Fomalhaut B is horrifying in a very specific way. It reminds us that the universe is deceptive. Our instruments are powerful, but they are limited. We see shadows and interpret them as substance. We see a blink of light and assume a world. Fomalhaut B is a cautionary tale, a reminder that not everything that twinkles in the darkness is a star, and not every moving dot is a planet. Sometimes it is just dust. Sometimes it is the aftermath of a great and silent destruction, a catastrophe that we can only observe in its fading echo. Now, we travel to the most ancient world on our list, Captain B. It is only 13 light-years away, practically in our backyard, and it is one of the oldest known potentially habitable planets. Captain B orbits a red subdwarf star called Captain Star, which is about 11.5 billion years old. That is old. The universe itself is only 13.8 billion years old. Earth is a whippersnapper at 4.5 billion. Captain B has existed for more than double the time of our entire planet, our entire solar system, our entire evolutionary chain. It is a relic of the early universe. The planet is a super-Earth, probably rocky, and it sits in the habitable zone of its star. Its host star is very dim, radiating 250 times less light than our Sun. So, even though Captain B is incredibly close to its star, closer than Mercury is to our Sun, the conditions on its surface could be moderate. Estimates put the temperature somewhere between a frigid 50 degrees Celsius on the dark side and a balmy 10 degrees Celsius on the sun-facing side. Liquid water could exist. It has a relatively high Earth similarity index, meaning it is one of the most Earth-like worlds we have found. And it has had 11.5 billion years to evolve life. Let that sink in. On Earth, life appeared relatively quickly, within a few 100 million years of the planet's formation. Then it took another 3.5 billion years to produce complex multicellular organisms, and then another 600 million years to produce us beings who can ask these questions. If life emerged on Captain B with similar timing, it could have had an 8 billion year head start on us. That is almost inconceivable. It is more than enough time for life to evolve intelligence, to build civilizations, to rise and fall over cycles that dwarf our own recorded history. But here is the horror. We see no evidence of life. The planet is silent. The vast age of Captain B is not a guarantee of life. It is a void. It is an empty stage waiting for a play that may never have begun. Or, perhaps more terrifyingly, the play did begin. Life did emerge. It evolved, thrived, and then something ended it. The planet is a tombstone, a monument to a biosphere that rose and fell long before our own ancestors crawled out of the primordial soup. We may never know. It is a quiet horror, the horror of profound, unanswered questions. This brings us to the final, overarching terror, the possibility of alien life adapting to these extreme conditions. We think of life as fragile. We need water, oxygen, a specific temperature range, but we are biased. We are creatures of a comfortable Goldilocks zone. The truth is, life is incredibly resilient. Here on Earth, we have found extremophiles, organisms that thrive in boiling volcanic vents at the bottom of the ocean, in acidic pools, in Antarctic dry valleys, in the radioactive cores of nuclear reactors. If life can exist in those places, why not on a world with a thick atmosphere of carbon dioxide? Why not beneath the ice of an ocean on a moon like Europa, or in the methane lakes of Titan? The planets we have discussed are horrifying to us, but to a hypothetical life form evolved specifically for those conditions, they might be paradise. On Coro T7b, life might exist in the narrow zone between the lava and the frozen dark, feeding on the thermal energy of the rock rain. On PSO J319.5-22, life might float in the thick iron-rich clouds, absorbing the faint infrared glow from the planet's core. On WASP 12b, life might exist in the stratosphere, organisms that feed on the intense stellar radiation and the carbon compounds in the atmosphere. The universe does not care about our comfort. It is a laboratory of possibilities. The horror is not that these worlds are dead. The horror is that they might be alive in ways we cannot even imagine. We might be the fragile ones, the exception, hidden away in our little blue bubble, while the rest of the universe teems with life that is utterly alien, utterly indifferent, and utterly terrifying. As we conclude this journey, look up at the night sky again. The stars are not just points of light. They are suns, and around many of them, worlds are turning. Some of those worlds are gentle, some are violent, some are dying, some are ghosts, some are ancient and silent. Each one tells a story. The story of a universe that is magnificent, dangerous, and deeply, deeply strange. The horror is not just in the fire or the darkness, it is in the scale. It is in the absolute indifference of it all. The universe does not care if we exist. It does not care if we find these planets. It simply is. And we, the fragile observers on our speck of dust, are very, very lucky to be here to witness the terror and the beauty of it all. The search continues. Every year, new planets are discovered. Every year, we find new ways to be horrified. And every year, we grow a little smaller, a little humbler, and a little more amazed. The most horrifying planets are not just out there. They are a mirror reflecting our own fragility back at us, and that, perhaps, is the greatest horror of all. There is a deeper layer to this horror, one that we must peel back if we are to truly understand what we are looking at when we point our telescopes at these distant worlds. The horror is not simply the temperature, the pressure, the radiation, or the isolation. The horror is the method by which we even know these planets exist, because we do not see them. Not really. We infer them. We measure a tiny dip in a star's brightness, a transit, and from that single, fleeting dimming, we calculate a planet's size, its orbital period, its distance from the star. We measure a slight wobble in the star's spectrum, radial velocity, and we deduce the planet's mass, its gravity, the very tug it exerts on its sun. We are detectives, piecing together the crime scene of the cosmos from shadows and echoes. Let that sink in for a moment. Every terrifying detail we have described, the rock rain, the iron clouds, the diamond cores, the shredded atmosphere, is not a direct photograph. It is a model. It is an educated guess based on the faintest of signals. The temperature of Coro T7b is estimated using the star's luminosity and the planet's proximity, but we have never measured it directly. The composition of WASP-12b's atmosphere is deduced from spectroscopy, reading the colors of starlight as it passes through the planet's thin outer envelope. The existence of PSO J317.522's iron rain is a theoretical prediction based on the planet's temperature and the known physics of gas giant atmospheres. We are building these worlds in our minds, and the scaffolding is mathematics, the mortar is probability, and the result is a cathedral of fear. And this brings us to a crucial question. How reliable are these discoveries? How do we know we are not being fooled again, like we were with Fomalhaut-B? The answer is both reassuring and terrifying. Reassuring because the methods have been cross-checked thousands of times. A transiting planet that also produces a radial velocity signal is considered confirmed. The Kepler mission alone discovered over 2,600 confirmed exoplanets using this dual approach. The transit method, which we have mentioned repeatedly, works because a planet crossing the face of its star blocks a tiny fraction of the star's light. The bigger the planet, the more light it blocks. The orbital period tells us how far it is. If we see the same dip at regular intervals, we have a candidate. Then radial velocity confirms the mass. And, if we are lucky, we can even observe the planet's thermal emission or reflected light directly, like we did with the rogue planet. But here is the terror. The vast majority of exoplanets are not detected this way. The transit method requires the planet's orbit to be aligned with our line of sight, a geometric coincidence that happens for only a small fraction of systems. For every planet we see transit, there are dozens that never cross the face of their star from our perspective. We are blind to them. We are looking at a tiny biased sample. The universe is teeming with planets, but we only see the ones that happen to line up perfectly. It is like standing in a dark forest and seeing only the fireflies that flash directly in front of your face, and assuming that's all there is. The true number of planets in our galaxy alone is estimated to be in the trillions, and we have catalogued a few thousand. We are barely scratching the surface. So when we talk about the most horrifying planets ever discovered, we must acknowledge that we are talking about the most horrifying planets that happen to be detectable. What lurks in the darkness beyond our observational window? What worlds spin in orbits that never bring them between us and their star? What hellish landscapes exist on planets that are too small, too dim, too far away for our current instruments to catch? The horror of the unknown is often greater than the horror of the known. We know about WASP-12b because it is dying in front of us. But what about a planet that died 1 billion years ago, leaving only a ghostly ring of debris? We know about Captain B because it is close. But what about a world identical to Earth, 10,000 light-years away, with a civilization that collapsed into silence before our ancestors learned to walk upright? We will never know. The universe is vast and our eyes are small. Let us now consider the distances we have been throwing around. We said Coro T7b is relatively close at 489 light-years. We said PSO J317.522 is 80 light-years away. We said Captain B is 13 light-years. For context, 13 light-years means that light from Captain's star, traveling at 186,000 miles per second, takes 13 years to reach us. That is our neighbor. But the nearest star system beyond our Sun, Proxima Centauri, is 4.2 light-years away. So Captain B is 3 times farther than that. It is still incredibly far by human standards. To send a spacecraft there at our current fastest speeds, about 40,000 miles per hour, would take over 200,000 years. These close planets are unreachable. They are islands in an ocean we cannot cross. The horror of distance is that we will never stand on these worlds, never confirm our models, never see the rock rain with our own eyes. They will remain theoretical, mathematical, abstract. And yet, they are real. They exist right now, spinning and burning and freezing, utterly indifferent to our curiosity. And that brings us back to the question of life. We speculated about life adapting to extreme conditions, but we must be more precise. What do we mean by life? On Earth, life as we know it requires liquid water, a source of energy, and a supply of organic molecules. That is the biochemical constraint. But there could be life based on silicon, or on ammonia, or on methane. There could be life that thrives in liquid ethane at 180 degrees Celsius, like on Saturn's moon Titan. There could be life that uses sulfur instead of oxygen, like the extremophiles in volcanic vents. The universe is chemically rich. The building blocks of life, carbon, hydrogen, oxygen, nitrogen, are the most abundant elements in the cosmos after hydrogen and helium. The ingredients for life are everywhere. The question is whether the conditions on these horrifying planets ever allowed those ingredients to come together in a self-replicating, evolving system. Consider a planet like Corot 7b. The day side is a lava ocean. The night side is a frozen wasteland. The only temperate zone might be a ring of twilight, a thin strip along the terminator where the temperature is just right for liquid rock, but not liquid water. That strip is constantly bombarded by heat from the day side and cold from the night side. The atmosphere, if any, is thin and composed of vaporized silicates. Could life exist there? Some scientists have proposed rock-eating organisms that metabolize the minerals of the lava, using the extreme heat as an energy source. It sounds like science fiction, but we have found bacteria on Earth that live inside solid rock, feeding on the chemical energy released by radioactive decay. The principle is the same. Life finds a way. It adapts. It colonizes niches we would never think possible. The horror of Corot 7b is not that it is dead. It is that it might be alive with forms so alien we would not recognize them as living. They might not have DNA. They might not have cells. They might be a thin, self-organizing film of metallic compounds that reproduces through thermal cycling. They might be a planetary-scale chemical reaction that we would dismiss as geology. Similarly, on a rogue planet like PSO J319.522, the interior still retains heat from formation and radioactive decay. Deep beneath the iron clouds, there could be a liquid ocean of metallic hydrogen, or a layer of high-pressure water. If that planet has a rocky core, it could be geologically active, with hydrothermal vents on the ocean floor. Bacteria on Earth thrive in such vents at pressures hundreds of times greater than at the surface. Why not on a rogue planet? The absence of sunlight is not a problem for chemosynthesis. Life could exist in the dark forever, powered by the planet's internal heat, never seeing a star, never knowing that there is an outside universe. Look up on a clear summer night, away from city lights, and you might see a faint smudge of the Milky Way stretching across the sky. Somewhere between the constellations Aquila and Sagittarius, there's a tiny patch of darkness called scutum, Latin for shield. It's almost invisible to the naked eye. No bright stars mark it, No ancient myths celebrate it. To most people, it's just empty space. But that emptiness is a lie. Behind that quiet shield, at the far edge of our galaxy's busy inner arm, something impossible is burning. A star so enormous that if you swapped it with our Sun, its outer layers would reach beyond the orbit of Saturn. A star whose volume could swallow 10 billion suns. A star so big that according to the standard equations of stellar physics, it should not be able to exist. This is the story of the largest star we have ever found, a red supergiant named Stephenson 2-18. And it turns out that its size has forced astronomers to question what they thought they knew about the limits of nature. We will walk through the discovery, the controversy, the physics that seems to forbid stars this large, and the unsettling possibility that this monster might already be dead. It all started in the late 1980s with an astronomer named Charles Stephenson. He wasn't chasing records. He was doing a routine survey of the sky in infrared light, looking for cool red stars that are invisible to the human eye. Most of what he found were ordinary red dwarfs and distant giants, nothing that would make headlines. But in 1990, Stephenson aimed his telescope at that patch of sky in Scutum. He was using a technique called objective prism spectroscopy, which spreads starlight into rainbows so you can identify the type of star. When he developed the photographic plates, he saw something odd, a tight cluster of deep red signatures, all in one small region. They were the unmistakable fingerprints of red supergiants, dying stars that have puffed up to enormous sizes. He had discovered a cluster he later named Stephenson 2, and inside it he numbered the brightest star as number 1. That star would eventually become known as Stephenson 2-18, but at the time, nobody paid much attention. Stephenson published his catalog quietly. For 17 years, almost nobody touched it. Then, in 2007, a team led by astronomer Ben Davies took a serious look. They confirmed that the cluster was packed with red supergiants, eventually counting 26 confirmed members. That is the highest concentration of red supergiants known anywhere in the Milky Way. To put it in perspective, our entire galaxy has only about 200 catalogued red supergiants. Finding 26 in one small cluster is like walking into a single classroom and finding 26 lottery winners. It shouldn't happen by chance. Something must have triggered a baby boom of massive stars in that region about 14 to 20 million years ago. And now they are all entering their final, swollen phase at the same time. Among these giants, one star stood out. It was far brighter than the others, so bright that it shouldn't statistically be there. That star, Stephenson 2-18, is the focus of our story. At this point, you might be wondering, just how big is it? The number most often quoted is 2,150 solar radii. In plain English, that means you would have to line up 2,150 of our suns edge to edge to span the diameter of this star. But numbers alone fail to capture the scale, so let's do a thought experiment. Take our sun, which is already enormous. You could fit about 1 million Earths inside it. Now imagine replacing the sun with Stephenson 2-18. Mercury, Venus, Earth, Mars, gone, vaporized in seconds. The asteroid belt, gone. Jupiter, the giant of our solar system, would be inside the star. Saturn, with its beautiful rings, would be skimming the surface, some calculations placing it just barely inside. Light takes about 2.5 hours to cross this star from one side to the other. That's a photon born in the core that will be older than your morning coffee by the time it reaches the other edge. The volume is even more mind-boggling, roughly 10 billion times the volume of the Sun. That's a factor that our brains simply can't hold. But the star's density is the opposite extreme, because all that volume is filled with extremely thin gas. The average density of Stephenson 218 is less than the density of the air in your living room. In fact, it's comparable to the upper atmosphere of Earth. The star is mostly empty space, held together by a delicate balance of gravity and pressure. Now here's where physics enters the picture. In 1961, a Japanese astrophysicist named Chushiro Hayashi calculated that there is a hard upper limit to how large a stable star can become. He showed that as a star's surface cools below a certain temperature, around 3,500 Kelvin, the way energy moves through its outer layers changes. The outer envelope becomes fully convective, like a pot of boiling water. And beyond that point, the equations for hydrostatic equilibrium, the balance between gravity pulling in and pressure pushing out, simply have no solution. In other words, a star cannot hold itself together if it gets too big. This boundary is called the Hayashi limit, and for decades it has been considered a firm wall. The theoretical maximum radius for a red supergiant is roughly 1,500 times the Sun. Stephenson 2-18, with its claimed 2,150 solar radii, sits well past that wall. If the measurements are correct, this star is doing something the textbook equations say is impossible. But does it really break physics? Not in the literal sense. No star can violate the laws of thermodynamics. What it does is challenge our models. The Hayashi limit is derived from certain assumptions: spherical symmetry, no magnetic fields, no rotation, no mass loss. Real stars are messier. Stephenson 2-18 might be showing us that under extreme conditions, rapid mass loss, chaotic pulsations, very low surface gravity, the limit can be stretched, at least temporarily. Alternatively, the star might be in a brief unstable phase, swollen to this size just before it either collapses or blows off its outer layers. One way or another, this star is a test of our understanding. And the controversy isn't just philosophical. It hinges on a single frustrating measurement. Almost every wild claim about Stephenson 2-18 traces back to one number: its distance. In astronomy, distance is the foundation. Once you know how far away a star is, you can convert its apparent brightness into true luminosity, its angular size into physical radius, its motion into real velocity. Get the distance wrong, and everything derived from it is wrong by the same factor. For Stephenson 2-18, the distance is a mess. When Charles Stephenson first estimated the distance to the cluster, he calculated about 30 kiloparsecs, nearly 100,000 light-years. That would have placed it on the far side of the Milky Way, almost outside our galaxy. But later studies, using better methods, brought the cluster much closer, around 5.8 kiloparsecs, or about 18,000 to 19,000 light-years. That's still far, but well within the galaxy. The problem is that Stephenson 2-18 itself might not belong to the cluster. Its velocity through space, measured by the Doppler shift of its light, is about 89 kilometers per second. The average of the other cluster stars is about 109 kilometers. That 20 kilometers difference is large enough to suggest that the star could be a foreground or background object superimposed by chance. If it's in the foreground, it's closer and smaller. If it's in the background, it's even larger. If it belongs to the cluster, the headline 2,150 solar radii stands. For years, astronomers have argued this point. The most careful analysis of the star's motion, combined with the fact that its radial velocity has remained stable, suggests it's not being pulled by a binary companion. Some researchers think the 20 km/s difference is caused by the star's own outflow. We might be measuring the speed of gas streaming toward us, not the star itself. This explanation is plausible but unproven. The upshot is this: the distance to Stephenson 2-18 has an uncertainty greater than 50%. It could be anywhere from about 9,000 light-years to 30,000 light-years. Move the star within that range, and its radius could shrink to a few hundred solar radii, still big, but not record-breaking, or swell to over 3,000 solar radii. The reigning champion is built on shaky ground. Despite these uncertainties, the star's behavior tells us that whatever its exact size, it is extraordinary. Observatories around the world have monitored its brightness for years, and the light curve is chaotic. Stephenson 2-18 pulsates irregularly, with no clean period. Its surface temperature, around 3,200 Kelvin, is cool enough that molecules like titanium oxide can survive in its atmosphere, another sign that it is pushing the boundaries of stellar stability. The star is also losing mass at a ferocious rate. Infrared observations reveal a vast shell of dust around it, material that was once part of the star's outer envelope. The mass loss rate is among the highest ever measured for a red supergiant, comparable to the extreme star VY Canis Majoris. Every year, this star sheds the equivalent of a small planet. Over the next tens of thousands of years, it will peel itself down to its core. That mass loss is driven by multiple mechanisms. Radiation pressure from the star's enormous luminosity pushes on gas and dust. The low surface gravity makes it easy for material to escape. And the star's own pulsations act like a slow-motion kick, launching gas upward with each cycle. The result is a stellar wind that is not steady but episodic, bursts of high outflow alternating with quieter periods. The surrounding dust shell is not smooth. It has clumps and asymmetries, recording the star's recent history of violent outflows. So what is really happening inside this star? Deep in its core, fusion is still going on, but the fuel is running out. Stephenson 2-18 likely began its life as a star with a mass between 20 and 40 times that of the Sun. It burned through its hydrogen in a few million years, then helium, then carbon, each stage shorter than the last. Right now, it is probably fusing helium into carbon and oxygen, or it may have already moved on to carbon burning. The exact stage is unknown, but we know it is near the end. A massive star dies when its core turns to iron. Iron cannot fuse to release energy. Instead, fusion stops. The core collapses under its own gravity in less than a second. The collapse triggers a shock wave that tears the star apart, a supernova. For Stephenson 2-18, that moment could come at any time. In cosmic terms, any time could be tomorrow or 100,000 years from now. But because the star is 18,000 light-years away, the light we see today left it during the last ice age. It is entirely possible that the star has already exploded, and the flash of that explosion is racing toward us at the speed of light. One evening, without warning, a new star will appear in the constellation Scutum, so bright it will be visible in daylight. It will outshine every other star in the night sky for weeks, then gradually fade over months. When that happens, every controversy about Stephenson 2-18 will be settled in a single moment. The supernova will tell us its true mass, its true structure, and the nature of its explosion. Neutrino detectors deep underground will pick up the first signal hours before the light arrives. Telescopes around the world and in space will capture the entire event in exquisite detail. It will be one of the most studied astronomical events in human history. And what will be left behind? A neutron star or a black hole, depending on the star's final mass. If the core is below about 2.5 solar masses, it becomes a neutron star, a ball of neutrons about the size of a city, spinning rapidly, maybe a pulsar. If the core is heavier, it collapses all the way to a black hole, an object from which no light can escape. Either way, the star that once challenged our theories will become a compact remnant, while its enriched debris will seed the surrounding space with heavy elements, carbon, oxygen, iron, the ingredients for future planets and life. Let's step back and think about what this star teaches us. The Hayashi limit is not a law of nature in the way that conservation of energy is. It is a mathematical boundary derived from assumptions about stellar structure. Stephenson 2-18, if its size is real, tells us that those assumptions are not absolute. Real stars can temporarily puff up beyond that limit, especially when they are losing mass rapidly and their outer layers are barely held together. The limit becomes fuzzy, not a wall, but a narrow region where stability is rare but not impossible. This is a recurring theme in astronomy. The universe is more inventive than our models. We build theories based on average conditions, and then nature throws a curveball. Stars like this one force us to refine our equations, to include more realistic physics, rotation, magnetic fields, dynamic atmospheres, episodic mass laws. Each outlier reveals a gap in our understanding. There are other giant stars that also flirt with the Hayashi limit. WOH G64 in the Large Magellanic Cloud, VY Canis Majoris, NML Cygni. Stephenson 2-18 is the most extreme candidate, but it is not alone. Collectively, these monsters are teaching us that the upper end of stellar size is not a hard cutoff, but a gradual, messy boundary where stars become increasingly unstable. The title of biggest star ever found is a moving target. Better measurements often demote previous champions. UY Scuti once held the crown with an estimated 1,700 solar radii, until Gaia parallax measurements slashed it to about 755. Stephenson 2-18 might suffer the same fate when more precise data arrives. Or it might keep the crown and force a rewrite of the textbooks. Either way, the star itself doesn't care what we call it. It sits there in the dusty depths of Scutum, burning through its last reserves, shedding its skin, pulsating, waiting for the final collapse. Its light, ancient and red, reaches us across 18,000 years of space, carrying the story of a star that seems to defy the rules. And that story is far from over. Every night that we look up at that faint, empty patch of sky, we are looking at a ticking clock. Somewhere out there, the largest star we know might already be gone. The light of its death could be on its way right now, crossing the interstellar void, carrying the answer to every question we have asked about it. When that light finally arrives, whether next week or 100 millennia from now, it will be a cosmic event that unites the entire world in wonder. It will remind us that the universe still holds surprises, that our understanding is always incomplete, and that the biggest stars, even when they challenge our limits, eventually bow to the same physics that holds every atom together. Stephenson 2:18 is not a break in the laws of nature. It is a revelation of how much more we have to learn. And in the meantime, the star burns on, indifferent to our debates, quietly writing its own final chapter. But the story does not end with that final chapter. The real impact of Stephenson 2:18 stretches far beyond its own fiery death. It is a window into a process that shapes the entire galaxy, one that we are only beginning to understand. Every red supergiant that explodes flings heavy elements into space: carbon, oxygen, silicon, iron. These are the building blocks of planets and of life. The star that seems to defy physics is actually a cosmic factory, manufacturing the raw materials for future worlds. If it has already exploded, its debris is now mixing with interstellar gas, enriching the Scutum Centaurus arm for generations of stars yet to be born. The very atoms that will one day form new rocky planets, maybe even new biospheres, were forged in the core of this singular giant. That is the deeper truth behind the headline. The largest known star is not a freak accident. It is a natural outcome of a young, massive cluster that formed in a starburst event millions of years ago. Its existence tells us that star formation can produce truly extreme objects, even if they are rare. By studying Stephenson 2:18, astronomers learn about the conditions in its birthplace, the density of the original gas cloud, the rate at which stars formed, the initial mass function that governed which stars were born. Every piece of data we extract from this star is a clue to the history of that entire region of the galaxy. There is another lesson, one that applies to every branch of science. Certainty is hard to come by. The star's size, mass, luminosity, age, distance, all of them come with asterisks. The public often expects clean answers, but the reality is that astronomy, like all frontier science, is messy. The uncertainties are not failures. They are honest reflections of the limits of our instruments and models. And that humility is a strength. It means we are always ready to be corrected by new data. Stephenson 2:18 has already been corrected once, from Stephenson's 1990 distance to the modern value, and it will be corrected again. The headline we use today might be outdated tomorrow. That is not a flaw in the science. It is the engine of progress. So where do we go from here? The next few years will be pivotal. The James Webb Space Telescope has already begun observing the most dust-obscured regions of the Milky Way. Its infrared vision cuts through the shrouds that hide stars like Stephenson 2:18. In the coming cycles, astronomers will use Webb to measure the star's spectral energy distribution with far greater precision, to map its dust shell in detail, and perhaps to resolve surface features that are currently blurry. The extremely large telescope, with its 39-meter mirror, will be able to detect the star's photosphere as more than a point of light. It might see the giant convection cells, the asymmetries, the pulsations. For the first time, we will have direct images of the largest known star. And then there is Gaia. The Space Telescope continues to map the galaxy with ever-increasing accuracy. Future data releases will refine the parallax of Stephenson 2:18, reducing the distance uncertainty from 50% to maybe 10% or less. When that happens, the star's true size will become clear. If it turns out to be 1,500 solar radii, the controversy fades. If it stays at 2,150, the textbooks will need a new chapter. Either outcome is valuable because it forces us to confront the limits of our knowledge. Meanwhile, the star itself does not wait. Every second, it burns through thousands of tons of nuclear fuel. Its core slowly shrinks and heats. The surrounding envelope gets looser. The pulsations may become more violent, the mass loss more extreme. At some point, the core will reach the end of its fusion chain, and then, in a few minutes of cosmic violence, the star will become something else entirely. Imagine that moment. Deep inside, a sphere of iron about the size of Earth, weighing maybe 2 solar masses, suddenly passes the threshold. The iron core can no longer support itself. The pressure becomes so intense that electrons are forced into protons, turning them into neutrons. The core collapses from thousands of kilometers in diameter to just a few dozen kilometers in less than a second. The infalling outer layers slam into this rigid neutron core and bounce. A shock wave forms, blasting outward. In the next few hours, it tears through the rest of the star. The energy released is so colossal that for a brief time, the explosion outshines the combined light of every other star in the Milky Way. A single point in Scutum becomes the brightest object in the night sky, visible even in daylight. That is the future of Stephenson 218. And because the star is 18,000 light-years away, the light from that explosion is probably already on its way. The neutrino burst from the core collapse will arrive hours ahead of the visible flash. Underground detectors around the world, Super Kamiokande in Japan, Ice Cube at the South Pole, will record a brief spike in events. Astronomers will get a warning. Then the sky will change. For the public, this will be an unforgettable event. People will step outside and see a new star, brighter than Venus, casting shadows. It will be visible in cities, through clouds, even during twilight. For weeks, it will dominate conversation. Social media will light up. News channels will anchor entire segments around it. Scientists will scramble to point every available telescope at it. The data flood will be unprecedented. We will measure the explosion's chemistry, its geometry, its light curve, with exquisite detail. We will finally know the true mass of the progenitor. We will see whether it formed a neutron star or a black hole. We will watch the remnant fade into a supernova remnant that will glow in radio and X-rays for thousands of years. And after the excitement fades, the legacy remains. The heavy elements ejected by that supernova will drift through the Scutum Centaurus arm. 1,000,000 years from now, some of that carbon and oxygen will be incorporated into a new generation of stars and planets. In 1,000,000,000 years, an alien astronomer in that region might look up at a sky enriched by the death of Stephenson 218. They will never know the name we gave it, but they will be made of its atoms. That is the ultimate meaning of this star. It is not just a record holder or a source of controversy. It is a link in the chain of cosmic evolution. It reminds us that the universe is a place of constant change, that even the largest, most stable-seeming objects are temporary, and that our own existence depends on the violence that ends such stars. So, the next time you look up at the constellation Scutum, that faint, almost invisible shield in the summer sky, remember what hides behind its quiet patch of darkness. A star that could swallow our entire solar system out to Saturn. A star that challenges the equations we thought were settled. A star that is bleeding its outer layers into space, preparing for a spectacular death. A star that might already be dead, its final flash racing toward us at the speed of light. And remember that the story of Stephenson 2-18 is not a closed chapter. It is an open investigation, a testament to how much we still don't know about the vast, intricate cosmos we call home. The biggest star ever found might not be the biggest star there is. There could be others, even more extreme, hidden in the dust of more distant spiral arms. The galaxy is full of secrets. Every time we push our instruments further, we find something that makes us rethink everything. That is the beauty of science. It never settles. It never stops asking. And as long as stars like Stephenson 2-18 burn, they will keep challenging us to look deeper, measure more carefully, and imagine more boldly. The biggest star ever found is bigger than physics allows, or so it seems. But physics, like the star itself, is always evolving. And the truth, when we finally get it, will be more wonderful than any headline. And perhaps that is the greatest lesson of all. The universe does not hand us tidy answers. It hands us puzzles wrapped in dust and distance. Stephenson 2-18 is not a failure of physics. It is an invitation to refine it, to stretch our understanding a little further. Every measurement, every debate, every new observation adds another thread to the tapestry. The star burns on, waiting, and so do we, patiently, with telescopes aimed at the shield, ready for the next revelation. In the vast, indifferent theater of the cosmos, there are stars that burn, stars that fade, and stars that destroy. But among the hundreds of billions of stellar bodies that populate the Milky Way, one type of object holds a special, terrifying distinction. It is not the largest, it is not the brightest, it is not even the most massive, but it is, by many measures, the most dangerous star in our galaxy. This is a story about a cosmic killer that spins at a rate that defies comprehension, a corpse of a star that packs the mass of a sun into the space of a city, and a gravitational monster that, under the right circumstances, could snuff out our entire solar system in a heartbeat. This is the story of Pulsar J09520607, the heavyweight champion of neutron stars and the galaxy's ticking time bomb. To understand why this particular object is so dangerous, you first need to understand the extreme physics of neutron stars. Imagine the most violent event you can conceive: a supernova, the explosive death of a star at least 8 times the mass of our Sun. When such a star exhausts its nuclear fuel, the core, no longer supported by the outward pressure of fusion, collapses inward at a staggering fraction of the speed of light. Within a second, the core, which was once roughly the size of Earth, is crushed into a sphere just over 6 miles across. This is not a gradual process. The implosion is so violent that the protons and electrons in the core are literally squeezed together, merging to form a sea of neutrons. The resulting object is a neutron star, a ball of the densest observable matter in the universe. Let me give you a specific number to put that density into perspective. A single teaspoon of neutron star material, about 5 milliliters, would weigh roughly 1 billion tons on Earth. That is not a vague comparison to mountains or skylines. That is the mass of a mountain, a literal pile of rock that rises miles into the sky, compressed into a spoonful. But density is only the beginning. The gravitational field at the surface of a neutron star is so intense that if you were foolish enough to drop a small object, say a single penny, from a height of just 1 meter, it would hit the surface with the force of a nuclear explosion. The impact would release energy equivalent to detonating roughly 1,000 hydrogen bombs. And this is just the baseline for a normal neutron star, one weighing about 1.4 times the mass of our Sun. Now, consider pulsar J09520607. This is not a normal neutron star, located roughly 5,000 light-years from Earth in the constellation Sextans. This object is a record breaker. It has a mass of approximately 2.35 solar masses. That is nearly 2.4 times the mass of our entire Sun, squeezed into a sphere that could comfortably sit within the boundaries of New York City. To achieve this mass, the core of the original star had to be enormous. But the real story of how it got so heavy lies in its hungry parasitic behavior. Pulsar J09520607 spins at a rate of 707 revolutions per second. Let me put that number in context. The blades of a typical kitchen blender spin at around 200 to 300 revolutions per second. A helicopter rotor, for comparison, spins at a sedate 5 to 7 revolutions per second. This pulsar is spinning more than 100 times faster than a helicopter rotor. At its equator, the surface is moving at a significant fraction of the speed of light. But why does it spin so fast? The answer involves a cosmic principle known as the conservation of angular momentum, and it plays out in one of the most violent relationships in the galaxy. Pulsar J09520607 is not alone. It has a companion, a white dwarf. A white dwarf is the leftover core of a star like our Sun, a dense, dim cinder that has exhausted its nuclear fuel. But in this system, the white dwarf is in a death spiral. The neutron star's immense gravity is literally tearing it apart. Material from the white dwarf, superheated plasma, streams across space and crashes onto the surface of the pulsar. This process, called accretion, transfers mass and, crucially, angular momentum from the companion to the neutron star. As the white dwarf is devoured, the pulsar spins faster and faster, like a figure skater pulling in their arms, except the skater is a stellar corpse with the destructive power of a supernova. This brings us to a critical point that often confuses people. How can a neutron star, which is made almost entirely of neutrons, have a solid iron crust? It seems paradoxical. The answer lies in the extreme pressure and temperature gradients at the surface. The neutrons in the star are not a uniform soup. At the surface, where the pressure is lower, a thin layer of normal matter can exist. This layer is composed of iron, the most stable element, forged in the supernova explosion that created the neutron star. As you descend deeper, the pressure increases and the iron atoms are crushed. The electrons are squeezed into the atomic nuclei, where they combine with protons to form more neutrons. At a depth of about half a mile, the iron lattice gives way to a dense fluid of neutrons with a sprinkling of protons and electrons. So, the crust is a solid crystalline shell of iron nuclei, roughly half a mile thick, floating on a sea of pure neutron fluid. It is a terrifying structure, rigid and brittle, subject to violent starquakes that can release more energy in a fraction of a second than our Sun produces in a year. Now, let us talk about the centrifugal force argument, because it is central to understanding why pulsar J09520607 is so dangerously close to its own destruction. A normal, non-spinning neutron star will collapse into a black hole if its mass exceeds a theoretical limit, typically thought to be around 2.1 to 2.3 solar masses. This is the Tolman-Oppenheimer-Volkoff limit, the point at which the neutron degeneracy pressure, the quantum mechanical force that keeps neutrons from crushing each other, can no longer hold up against gravity. But pulsar J0952-0607 is not normal. It is spinning at 707 revolutions per second. That rapid rotation generates a powerful outward centrifugal force. Think of it like a rock whirled around on a string. The faster you spin, the harder the rock pulls outward. For the neutron star, this outward pull acts against gravity, effectively propping the star up. It allows the star to hold together at a mass that would otherwise be fatal. Scientists calculate that this centrifugal support allows pulsar J0952-0607 to pack on an extra 10 to 20% of mass beyond the static limit. Without that spin, it would have already crossed the threshold and collapsed into a black hole. But this is not a stable situation. The spinning is not permanent. The pulsar is losing rotational energy through its intense magnetic fields and the beam of radiation it emits. As it slows down, the centrifugal support weakens. The star is essentially coasting on borrowed time. And there is another problem. It is still eating its companion. Every bit of mass it accretes from the white dwarf pushes it closer to the critical point. The pulsar is trapped in a vicious cycle. It spins faster because it eats, but eating makes it heavier, and slowing down will eventually remove the support that keeps it alive. When it finally collapses, it will form a black hole. But the collapse itself will be a cataclysmic event, a gravitational implosion that releases a burst of energy that could be detected across the galaxy. This type of pulsar is known as a black widow pulsar, named after the spider that consumes its mate. The companion white dwarf orbiting PSR J0952-0607 is being systematically obliterated. It orbits the pulsar at a speed of over 200 miles per second, completing a full orbit in just over 6 hours. The two objects are so close that the white dwarf is being evaporated by the pulsar's intense radiation and particle wind. Eventually, the white dwarf will be completely consumed, leaving the pulsar alone and dangerously close to the mass limit. At that point, the pulsar's fate is sealed. It will either collapse into a black hole immediately, or it will spin down slowly over millions of years and collapse later. Either way, the result is the same. So, what would happen if PSR J0952-0607 wandered into our solar system? Let us paint the most terrifying picture possible. Imagine this object, this spinning city-sized sphere of neutron soup, appearing in the orbit of Mars. The effects would be immediate and catastrophic. The pulsar's gravity would tear the solar system apart. Earth, Mars, and the gas giants would be yanked from their stable orbits. The planets would begin to drift, pulled into a chaotic dance around the tiny, super-dense invader. The Earth's atmosphere would be the first casualty. The intense radiation from the pulsar's beam, a lighthouse sweep of gamma rays and X-rays, would strip away our protective blanket. The oceans would boil. The surface would be sterilized within seconds, but the physical destruction would follow. As Earth's orbit destabilizes, it would be drawn closer and closer to the pulsar. Tidal forces, The same forces that cause our oceans to rise and fall would become so extreme that the planet itself would be torn apart. This is the Roche limit. At a certain distance, the gravitational pull of the pulsar would overcome the internal gravity of the Earth, ripping it into a stream of debris. The rock that was once our home would form a short-lived glowing accretion disk around the neutron star, a final molten funeral pyre. But the destruction would not stop there. The pulsar's gravitational influence would pull in the sun itself. But our sun would not simply be swallowed whole. The sun is a ball of gas, and as it approaches the neutron star, its outer layers would be siphoned off, forming a giant stream of plasma that spirals into the pulsar. This would be a process that could take thousands of years, but it would be a slow, agonizing death for our star. Eventually, the pulsar, having consumed the white dwarf that was its companion, and then the sun, would have accumulated even more mass. With the centrifugal support from its spin fading, it would cross the final critical threshold. The neutron star would collapse. In a fraction of a second, the city-sized sphere would vanish, replaced by a point of infinite density, a black hole. Our solar system would be gone, replaced by a single, silent gravitational pit. This scenario is purely hypothetical, of course. PSR J09520607 is safely thousands of light years away, locked in its deadly dance with its dying white dwarf. But it is not the only dangerous star out there. Far from it. The galaxy is filled with stellar monsters, each with its own unique way of causing destruction. And some of them are far, far stranger. Consider the magnetars. These are a rare and extreme subclass of neutron star, objects with magnetic fields so powerful that they beggar belief. A typical neutron star has a magnetic field 1 trillion times stronger than Earth's. That is already an incomprehensible number. A magnetar's magnetic field is another 1,000 times stronger than that. To give you a specific comparison, Earth's magnetic field is about half a Gauss. A fridge magnet is about 100 Gauss. A magnetar's magnetic field can be over 1 quadrillion Gauss d. This is a field so intense that it can warp the very shape of atoms. At a distance of a few thousand miles from a magnetar, the magnetic field would be so strong that it would disrupt the electron clouds in your body. Your atoms would be stretched into long, thin cylinders, aligned with the field lines. Your body would be literally torn apart at a quantum level. There would be no pain. There would be no awareness. You would simply cease to exist as a coherent entity, your matter dissolving into a plasma of distorted atoms. Magnetars are also prone to violent starquakes. The extreme magnetic field places enormous stress on the solid iron crust. Periodically, this stress becomes too much, and the crust cracks. The resulting quake releases a burst of energy that is staggering. In a fraction of a second, the magnetar can release as much energy as our sun produces in 100,000 years. This energy is released primarily in the form of gamma rays and X-rays, a blast of radiation that can travel across the galaxy. If a magnetar were located within 10 light-years of Earth, a single starquake would be enough to strip away our ozone layer, leaving the surface exposed to the full fury of the sun's ultraviolet radiation and cosmic rays. The result would be a mass extinction event on a scale that makes the dinosaurs' demise look like a minor inconvenience. Fortunately, the closest known magnetar, designated SGR 1806-20, is located about 8,000 light-years away. But distance is not always a guarantee of safety. In 2004, a magnetar named SGR 1806-20 unleashed a giant flare that was detected by satellites in our solar system. The burst was so powerful that it temporarily disrupted Earth's upper atmosphere, despite originating from the other side of the galaxy. The blast had the energy of 1 billion trillion nuclear weapons. If that same magnetar had been just 40,000 light-years closer, within a few thousand light-years of Earth, the effects would have been catastrophic. The gamma-ray burst would have damaged our satellite networks, caused widespread power grid failures, and exposed anyone on the surface to dangerous levels of radiation. Then there are the pulsars that are not just fast, but bright. The Vela pulsar, located just 1,000 light-years from Earth, is one of the brightest in the gamma-ray sky. It is a spinning neutron star that pulses 11 times per second, a relatively pedestrian spin rate compared to PSR J09520607. But what makes Vela special is the power of its radiation. Its gamma-ray emissions are about 200 times more energetic than those of a standard pulsar. The beam of gamma rays from Vela extends nearly 1 light-year into space. For comparison, that is 15 million times the distance between the Earth and the Moon. If a planet happened to drift into that beam, it would be instantly sterilized. The radiation would rip apart molecules, disrupt DNA, and turn the surface into a scorched, lifeless rock. The Vela pulsar is so close to us that scientists have been able to convert its radio pulses into an audio signal. It sounds like the roaring of a car engine or the beating of a massive mechanical heart. It is a constant, rhythmic reminder of the violence that hums quietly in our celestial backyard. Beyond neutron stars and magnetars, the galaxy is home to stars that are dangerous for entirely different reasons. Take Eta Carinae, a binary system located about 7,500 light-years away. This system contains a pair of hypergiant stars, one of which is incredibly unstable. In the mid-19th century, it underwent a massive eruption, ejecting several times the mass of our Sun into space. The resulting nebula, the homunculus, is a beautiful hourglass-shaped cloud of gas and dust. But if that star ever goes supernova, which it may do at any moment over the next few 100,000 years, the explosion will be one of the most powerful events in our galaxy. It could briefly outshine the combined light of all the other stars in the Milky Way. If Eta Carinae's rotational axis happened to be pointed toward Earth, the resulting gamma-ray burst could be devastating. Such a burst could damage our atmosphere, deplete the ozone layer, and trigger a mass extinction. The danger from Eta Carinae is not imminent, but it is a stark reminder that the galaxy is not a static, peaceful place. It is a dynamic, violent arena where stars live fast and die young. And then there are the stars that are not just dangerous because of what they do, but because of what they are. The galaxy contains stars that are so massive that they are on the verge of collapse into black holes. These are the Wolf-Rayet stars, hot, massive stars that are shedding their outer layers at a furious rate. They are near the end of their lives, burning through their remaining nuclear fuel with incredible intensity. A Wolf-Rayet star, like WR102, which is one of the hottest stars known, has a surface temperature of over 200,000 degrees Celsius. Its surface temperature is over 35 times hotter than the surface of the Sun. The radiation from such a star is so intense that it literally pushes matter away from itself, creating powerful stellar winds. Any planet in the vicinity would be vaporized, its atmosphere stripped, its surface melted to slag. These stars are ticking time bombs, waiting to explode as hypernovae, events that are even more powerful than standard supernovae, and that can leave behind a stellar mass black hole. But perhaps the most dangerous object in our galaxy, at least from a perspective of sheer concentrated malevolence, is the one we have already discussed. Pulsar J0952-0607 represents a unique confluence of factors. It is rapidly spinning, a quality that allows it to pack on extra mass. It is actively accreting matter from a companion, a process that will inevitably push it over the edge. And it is already so close to the critical mass limit that its existence is a precarious balancing act between centrifugal force and gravitational collapse. It is a star that is teetering on the brink of its own oblivion, dragging a doomed companion down with it. Let us delve deeper into the centrifugal force argument, because it is a subtle and beautiful piece of physics. When we say that rapid rotation allows the neutron star to support more mass, we are not just talking about a small correction. The effect is significant enough to allow the star to evade the Tolman-Oppenheimer-Volkoff limit by up to 20%. To understand how this works, consider the forces at play. Gravity is pulling every bit of the star inward, compressing it toward the center. The neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same space, pushes outward. In a non-rotating star, these two forces balance, but when the star rotates, a third force enters the picture. The centripetal force, which is the inward force required to keep matter moving in a circle, acts in the opposite direction of gravity, effectively reducing the net inward pull. At the equator, the effect is strongest. The star bulges outward. This bulging redistributes the mass, allowing a denser core to be hidden beneath a more extended surface. The math is complex, but the result is that a rapidly spinning neutron star can hold together at a mass that would otherwise be fatal. The spin provides a gravitational subsidy, but here is the catch. The spin is not free. The pulsar is emitting energy in the form of electromagnetic radiation and particle winds. This loss of energy causes the pulsar to slow down over time. Every time it loses a little bit of spin, it loses a little bit of that gravitational support. The mass, however, remains the same. So, as the pulsar slows down, it must contract slightly, becoming denser until it reaches a new equilibrium. But this can continue only so far. Eventually, the rotation becomes too slow to provide any meaningful support, and the star, now too massive to be held up by neutron degeneracy pressure alone, collapses. Pulsar J0952-0607 is not just any pulsar. It is one of the fastest spinning ever discovered. Its spin rate of 707 revolutions per second places it in a very elite club. To achieve that rate, it must have been accreting material from its companion for an exceptionally long time, or it must have been born with an unusually fast spin. Either way, it is a record breaker. And it is not just the spin that is extreme. Its mass is the highest ever confirmed for a neutron star. This combination of fast spin and high mass makes it a unique laboratory for studying the limits of nuclear physics. Scientists are still debating exactly how massive a neutron star can become before it collapses. PSR J0952-0607 is pushing those boundaries. Now, you might be wondering about the iron crust. How can a ball of neutrons have a solid surface at all? The answer takes us to the edge of our understanding of matter under extreme pressure. The crust is not made of neutrons. It is made of atomic nuclei, primarily iron, packed together in a crystal lattice. This lattice forms because at the surface of the star, the pressure is low enough that normal atomic structure can survive. But as you go deeper, the pressure and density increase. The atoms are squeezed closer together. The electron orbitals overlap, and the electrons are forced into the atomic nuclei, where they combine with protons to form neutrons. At a certain depth, typically around half a kilometer below the surface, the nuclei are so neutron-rich that they become unstable. The lattice dissolves, and the matter becomes a fluid of neutrons, with a small admixture of protons and electrons. This is the neutron star proper. The crust is fascinating because it is brittle. It can crack. When it does, it can trigger star quakes. These quakes are not like earthquakes. They release energies that dwarf any geological event on Earth. The energy released in a magnetar starquake is comparable to the entire energy output of the Sun over 1 million years. These quakes can cause the pulsar to suddenly change its spin rate, a phenomenon known as a glitch. Astronomers have observed glitches in many pulsars, and they are a valuable tool for probing the interior structure of these objects. All of this brings us back to the central question. Is PSR J0952-0607 the most dangerous star in our galaxy? It is a strong candidate. Its proximity to the mass limit, its rapid spin, and its predatory relationship with its companion make it a uniquely volatile system. But danger is a relative term. A magnetar is more immediately dangerous due to its magnetic fields, but they are rare. A Wolf-Rayet star will explode in a hypernova, but that event is far in the future. PSR J0952-0607 is dangerous because it represents a process that is ongoing. It is consuming a star. It is growing. It is approaching a critical phase. It is a star that is actively, right now, changing its own destiny. Perhaps the true danger of PSR J0952-0607 is not that it will destroy us. It is far too distant for that. The true danger is what it represents. It is a reminder that the universe is not a benign place. Stars are not just sources of light and heat. They are engines of destruction. They are the birthplaces of black holes. They are the factories that forge the elements, and every so often they create an object like this one, an object that dances on the razor's edge between stability and annihilation. It is a cosmic wonder and a cosmic warning. As we look through our telescopes, we are seeing a snapshot of a universe that is violent, chaotic, and indifferent to our existence. The night sky is not a peaceful canopy, it is a battlefield. And in that battlefield, PSR J0952-0607 is one of the most formidable weapons. It is a star that is literally spinning itself toward destruction, dragging a companion to its doom, and challenging our understanding of physics. It is the most dangerous star in our galaxy, not because it will kill us, but because it embodies the raw, untamed power of a universe that operates on scales and forces that we are only beginning to grasp. And the story does not end there. Our galaxy holds other secrets. There are stars that may harbor black holes in their cores, artifacts from the dawn of time. There are stars that are so faint and dense that they are nearly invisible, drifting through space like cosmic assassins. There are the remnants of stellar explosions that are still expanding, carving out bubbles of emptiness in the interstellar medium. Each of these objects tells a story of creation and destruction, of birth and death. Pulsar J0952-0607 is just one chapter, but it is a spectacular one. It is a star that, for a brief moment in cosmic time, is one of the fastest, most massive, and most dangerous objects in the galaxy. It will not last forever. Eventually, it will collapse, and a new black hole will be added to the galactic census. But until then, it spins, it pulses, and it consumes. It is a beacon of extreme physics, a lighthouse of danger, and a testament to the infinite creativity of a universe that can conjure such wonders from the ruins of dead stars. The most dangerous star in our galaxy may be thousands of light years away, but its shadow looms large, a reminder that we live in a cosmos where danger and beauty are often one and the same. Yet, for all the danger embodied by PSR J0952-0607, it is far from alone in the galaxy's rogues gallery. The Milky Way is littered with stellar corpses and unstable giants, each capable of unleashing destruction on scales that dwarf anything humanity has ever witnessed. Consider the neutron star binary system, PSR J0737-3039, located about 2,400 light-years away. It consists of two pulsars locked in a tight orbit that completes a full revolution every 2.4 hours. Both stars are dead, but their dance is not a peaceful one. They are slowly spiraling inward, losing energy through gravitational waves. In about 85 million years, they will collide. When they do, the merger will release a burst of energy equivalent to the combined output of 1 trillion suns. That kilonova would eject a cloud of heavy elements, including gold and platinum, across thousands of light-years. But any planet within a few hundred light-years would be sterilized by the gamma-ray flash and the subsequent blast of particles. The two pulsars are a ticking clock, and their collision will be one of the most violent events in our galaxy's future. Then there are the Black Widow and Redback pulsars, neutron stars that are actively destroying their stellar partners, just like PSR J0952-0607. But some of these systems are even closer to Earth. PSR J123+038, located about 4,500 light-years away, is a redback pulsar that has been observed switching between a state where it is slowly consuming its companion and a state where matter flows onto it in a furious torrent. This pulsar spins at 592 revolutions per second, and its companion is a low-mass star that is being relentlessly stripped. The system is so close that astronomers have watched its behavior change in real time, catching the moment when the accretion disk forms and then vanishes. If the pulsar ever pushes its mass over the limit, it will collapse into a black hole, and the entire system, including the half-eaten companion, will be swallowed. But the danger is not limited to neutron stars. There are massive stars that are so luminous they are literally blowing themselves apart. Take the star NGC3603A1, a binary system in the Carina Nebula. Each star is about 120 times the mass of our Sun. These are among the most massive stars known, and they are so close to each other that their surfaces almost touch. Their orbital period is barely 3.8 days. The radiation pressure between them is so intense that they are shedding mass at an enormous rate. When one of them goes supernova, it will not just explode, it will trigger a chain reaction in its companion, causing a second supernova within months. This double detonation will create a black hole and likely eject the remaining star at tremendous speed, turning it into a hypervelocity runaway. If that runaway star ever passed through the Oort cloud, it would send a hail of comets toward the inner solar system. The chances are low, but the potential for devastation is real. Even more unsettling are the stars that are simply too close for comfort. The red supergiant Betelgeuse, barely 650 light-years away, is in the final stages of its life. It has already shrunk and brightened erratically, leading to speculation that it may explode within the next 100,000 years, perhaps even tomorrow. When Betelgeuse goes supernova, it will be visible during the day, outshining the full moon. But the real danger lies in the radiation. If Betelgeuse's rotational axis points toward Earth, the gamma-ray burst could strip away our ozone layer, exposing the surface to deadly ultraviolet radiation from the sun. The event would be a natural catastrophe of global proportions. Yet Betelgeuse is not the most dangerous star in the galaxy. It is simply the nearest large star that might explode soon. The true monsters are farther away, but their effects can reach across vast distances. One such monster is the microquasar SS433, a stellar system that defies easy classification. SS433 is a binary system about 18,000 light-years away, consisting of a black hole or a neutron star, astronomers aren't entirely sure which, and a massive companion star. What makes it so dangerous is the way it accelerates matter. The compact object is pulling gas off its companion, but instead of forming a simple accretion disk, the system launches two narrow, oppositely directed jets of plasma at speeds approaching a quarter of the speed of light. Those jets are precessing like a wobbling top, completing a full rotation every 162 days. As they sweep through space, they carve out a region of violently disturbed gas and high-energy radiation. If Earth were ever caught in the beam of one of those jets, the blast of X-rays and gamma rays would be lethal, even from thousands of light-years away. But SS433 is not the only microquasar. A handful of others are known, and some are closer. Their ability to focus destructive energy into narrow beams makes them stealthy killers, a threat that can appear suddenly and devastate a planet without warning. Yet, for all these perils, the most dangerous star remains the one that embodies the very limit of stellar existence. PSR J09520607 is not the largest, not the brightest, not the most magnetic. It is, however, the star that sits at the knife edge between matter and oblivion. It is a cosmic tightrope walker, and it will eventually fall. When it does, it will create a black hole, a region of space where the laws of physics as we know them break down. That black hole will be the final legacy of a star that once spun faster than any other, that consumed its companion, and that defied collapse for a few precious million years. In the grand clockwork of the galaxy, this is just one more tick. But for those of us watching from our tiny blue planet, it is a reminder of the elegance and the ferocity of the universe we inhabit. The most dangerous star in our galaxy may not threaten us directly, but its existence teaches us that danger is woven into the fabric of space itself. And that is a lesson worth remembering every time we look up at the night sky. Out in the depths of the Milky Way, there is a star that refuses to behave like any other. It doesn't shine the brightest, it doesn't burn the hottest, and it doesn't sit quietly in some familiar corner of the night sky. Instead, it spins at speeds that would tear any ordinary object apart. It is so dense that a single teaspoon of its material would outweigh every mountain on Earth. But that is not even the worst part. The real problem is that this thing is unstable. It is balanced on a knife's edge. One wrong move, just a little more mass, just a little more pressure, and it will collapse into something even worse, a black hole. And the thing is, this is not some distant object on the edge of the observable universe. It is inside our galaxy right now, spinning, feeding, growing. Scientists have known about it for a while. They even gave it a name. But for all the data we have gathered, there is still one question they cannot answer. When is it going to blow? Or maybe the better question is, are we sure it hasn't already? When a massive star reaches the end of its life, it does not go quietly. It burns everything it has, trying to fight off the inevitable pull of gravity. And once its nuclear fuel runs out, gravity wins. The core collapses, the outer layers explode in a supernova, and what is left behind is something strange, something small, something impossibly heavy. What you get is a neutron star. It is not just dead, it is transformed. Now, a typical neutron star is not much bigger than a city, maybe 20 kilometers across. You could drive across it in under half an hour if you could somehow land on it without being crushed or vaporized. But in that tiny space, it holds more mass than our entire sun. That is like taking every person, planet, mountain, and ocean in our solar system and stuffing it into a sphere the size of Manhattan. Because it is so compact, a neutron star has insane density. 1 teaspoon of this stuff would weigh over 1 billion tons. That is more than the weight of every building in New York City combined. If you dropped a piece the size of a sugar cube onto Earth, it would not just sit there. It would punch straight through the crust, tear through the mantle, and keep going until it hit the core. It would not even slow down. But that is just the beginning. Some neutron stars spin, not slowly rotating like Earth, but ridiculously fast. They spin so fast that they flash beams of radiation across space, like the rotating light on a lighthouse. That is what we call a pulsar. Not because it pulses like a heartbeat, but because those beams sweep past us at regular intervals, and they look like pulses when we detect them. At first, scientists had no idea what they were. Back in 1967, when Jocelyn Bell first picked up the rhythmic signals of the first known pulsar, the team did not rule out aliens. That is how strange it was. Something in deep space was sending radio pulses with the timing of an atomic clock. Later, we figured it out. It was not E.T. It was something much weirder. These things spin at hundreds of revolutions per second. That is faster than the blades of a helicopter, faster than your kitchen blender, and in some cases, even faster than a jet turbine. They are cosmic flywheels that dwarf human-made machinery in both speed and endurance. And they do not slow down easily. Many of them have been spinning like this for millions of years. Now, why does a neutron star spin so fast in the first place? It comes down to a simple law of physics: conservation of angular momentum. Imagine an ice skater spinning on the ice. When they pull their arms in, they spin faster. The same principle applies to a collapsing star. When a massive star runs out of fuel, its core collapses from something the size of 1,000,000 kilometers down to something just 20 kilometers across. That dramatic shrinkage forces the core to spin up to incredible speeds, exactly like the skater pulling in their arms. The original star was rotating slowly, but after the collapse, all that rotational energy is squeezed into a much smaller volume. The result is a neutron star that can spin hundreds of times per second. This is not a mechanism that prevents black hole formation. It is simply a consequence of the collapse itself. The spin does not save the star from gravity. It just makes it more extreme. And here is where things get dangerous. Some pulsars do not just exist alone in the void. They find companions, not by choice, but by force, through a process called accretion. Nearby stars are caught in their gravitational grip. Over time, the pulsar gathers enough material from these unfortunate companions. The doomed companion, often a low-mass star, is stripped of its outer layers. Its matter is torn away in a searing stream of superheated plasma. This spiraling torrent of gas funnels into the pulsar, delivering a surge of energy. It spins faster, it gains mass, it becomes more extreme. Scientists call these black widow pulsars. Just like the spider, they consume their mate after mating. Only in this case, the pulsar does not just kill its companion, it eats it atom by atom. This process does not go on forever. There is a limit to how much mass a neutron star can hold. And once it gets too close to that line, the structure cannot hold anymore. The neutron pressure fails. Gravity takes over, and the pulsar collapses again, this time into a black hole. So, when we say some of these stars are dangerous, it is not because they are going to explode and send shock waves across the galaxy like a supernova. It is because they are already past the point of being ordinary stars. They are dense, powerful, spinning time bombs. And the one we are focusing on is not just any pulsar. It is the fastest spinning, heaviest neutron star ever discovered. And it is sitting right here in our own galactic neighborhood. Let me show you what makes this one different. Not all pulsars are equal. Most of them spin fast, yes. Most of them are dense and powerful. But every once in a while, astronomers find something that does not just fit the definition, it redefines it. One of those is called PSR J09520607. It does not have a flashy nickname, and it is not in a sci-fi movie. But what it does have is a resume that reads like a warning label from the universe itself. This thing spins at 707 revolutions per second. That is not a typo. Every second, it completes over 700 full rotations. You could not even blink that fast if you tried. It is so fast that its surface is moving at a significant fraction of the speed of light. And yet, it is not flying apart. Gravity holds it together, squeezing it so tightly that even atoms themselves do not exist on the surface anymore. The only thing left is neutron matter, crushed so hard that electrons and protons have merged. And as if that were not enough, it is also the heaviest neutron star ever discovered, nearly 2.4 times the mass of the Sun, all crammed into a space just 20 kilometers wide. That combination, extreme spin and near critical mass, is why this object is dangerous. Because here is the catch. Neutron stars are not supposed to weigh that much. The upper limit, the so-called Tolman-Oppenheimer-Volkoff limit, is estimated to be somewhere around 2.5 to 3 solar masses. Beyond that, the neutron pressure can no longer resist gravity, and the star collapses into a black hole. So, this one is close, really close. And we now know how it got this way. It was not born this massive. It ate its way here. Orbiting this pulsar is the dim, fading remnant of a star, a white dwarf that is being slowly ripped apart. Like a drop of water falling into a drain, its matter spirals toward the pulsar. Some of it falls in. Some of it forms a hot, glowing accretion disk. Either way, the pulsar gains mass. It also gains spin, just like an ice skater pulling in their arms, shrinking. The radius increases the angular momentum, and the more it feeds, the faster it spins. That is what makes these kinds of systems so extreme. The process does not just accelerate the pulsar, it puts it under pressure. Every gram of stolen matter is one step closer to the breaking point, one step closer to collapsing. Astronomers call it a black widow pulsar, and the analogy fits. The pulsar drains its partner until nothing remains. The white dwarf fades, the pulsar grows, and eventually there is nothing left but one unstill overfed neutron star waiting for a final push. Now, let us be very clear about something here. A white dwarf being cannibalized by a neutron star does not become a black hole on its own. In other contexts, white dwarfs in binary systems can accrete material, and if they cross the Chandrasekhar limit of about 1.4 solar masses, they can detonate in a spectacular Type Ia supernova. That is a different beast entirely. In this case, it is the neutron star itself that is gaining mass, inching ever closer to its own collapse into a black hole. The white dwarf is just the fuel source, the unfortunate victim being drained to feed the monster. So the danger here is not a supernova from the white dwarf. The danger is the neutron star becoming too heavy to exist. And here is where the reality of the situation sinks in. Unlike a supernova, which announces itself with a visible explosion, this collapse would not give us much warning. There would be no flash of light, no giant shockwave, just a sudden silence. The pulses stop, and in that silence, a black hole is born. We do not know when that will happen. Could be 1,000,000 years from now, could be tomorrow, could already have happened, and we are just waiting for the news to travel about 14,000 light years to reach us. And just so we are clear, this object is inside our own galaxy. It is not some distant curiosity in a faraway cluster. This is a ticking time bomb spinning at full throttle right here in the Milky Way. And the only reason it has not turned into a black hole yet is that it still holds itself together by sheer rotational momentum. The spin is buying it time, but eventually, time runs out. So let us say it happens. Let us say this pulsar finally crosses that invisible line. It pulls in just enough mass from its dying companion, and the delicate balance holding it together breaks. What exactly happens next? Well, the star does not explode, not in the way we are used to thinking about explosions. It collapses silently, instantly. One moment, it is a pulsar, spinning, beaming, pulsing like a galactic lighthouse, and the next, it is gone. The pulses stop. The light vanishes. The radio waves we have been picking up from Earth just cut off. No sound, no flash, just the flick of a switch. And what is left behind is a black hole. This is where the real physics kicks in. Unlike a supernova, which throws off most of the star's mass in a burst of light and gas, A pulsar collapsing into a black hole does not leave behind anything visible. There is no outer shell to eject. The material is already compacted as far as it can go, so the collapse is clean, direct, efficient. The mass is still there, but now it is hidden behind an event horizon. The gravitational pull becomes so strong that even light cannot escape. From the outside, the object becomes invisible, but its presence is still felt. Space around it warps, time slows near it, and anything too close falls in. Here is the good news. Even if this happened tomorrow, we would not feel a thing here on Earth, at least not for a while. This pulsar is about 14,000 light-years away, so if it collapsed today, the effects would not reach us for another 14,000 years. Technically, it might have already collapsed. We are still seeing the version of it that existed 14 millennia ago. The light we detect, the pulses we measure, are delayed snapshots from the past. But let us say, for the sake of curiosity, that it did collapse. What does that mean for the surrounding region of space? When a pulsar collapses into a black hole, it loses the structure that was keeping its radiation beams aligned. The regular pulse ends, but its environment does not instantly calm down. The accretion disk, all that material still spiraling in, keeps feeding it. But now, it is not feeding a pulsar. It is feeding a newborn black hole. This can briefly create something called a relativistic jet, an ultra-energetic beam of particles and radiation shooting out from the poles of the black hole, accelerated to near light speed by magnetic fields and rotational energy. If those jets happen to point anywhere near our direction, even from 14,000 light-years away, they could do real damage. That is not speculation. It has happened before. Astronomers suspect that a mass extinction event around 440 million years ago, the late Ordovician extinction, might have been caused by a gamma-ray burst from a nearby neutron star or black hole. It would not have hit Earth like a bomb. Instead, it would have silently fried our ozone layer, leaving the surface exposed to ultraviolet radiation from the sun. The result would have been a global collapse of ecosystems, especially marine life. Again, that is rare, unbelievably rare, and the odds of this pulsar's beam being aligned with us are even lower. Most of the time, these jets shoot off in random directions, and the vastness of space is usually enough to keep us out of the line of fire. Still, the point is, it can happen. And that is why scientists keep watching. But let us flip the question now. What if it did not collapse all at once? What if it kept growing slowly, pulling in more mass, increasing pressure, getting closer and closer to that critical point, while still spinning at 707 times per second? At some point, it reaches a stage where even the spin cannot save it. And then, in the blink of an eye, the entire structure gives way. Some models suggest this could unleash an extremely fast, short-lived burst of gravitational waves, ripples in space-time itself. Detectors like LIGO and Virgo might catch it, giving us a real-time signature of a pulsar collapsing into a black hole. That would be a scientific first, but it would also be a cosmic testament, a signal that one of the fastest, densest, most extreme stars in the galaxy just died a second death, quietly, without warning. And what replaces it? An invisible void, a gravity well from which no light can escape. The beam that once pulsed across the galaxy like a clock is gone. From a cosmic perspective, that is the end of the story. But from ours, it is just getting started. Because there is another kind of neutron star that does not wait for collapse to be dangerous, one that does not need to spin at 700 times per second to cause havoc. It is not faster. It is not heavier. It is just magnetic. You would think that a star spinning hundreds of times per second, weighing more than our sun, and teetering on the edge of collapse would be the worst-case scenario. But nature, as always, has a way of going further. Because there is another kind of neutron star out there. It does not spin as fast. It does not have to. It does not need a companion star to devour. It does not rely on beams of radiation to make its presence known. Instead, it warps the very structure of matter with something far more silent and far more terrifying. It is called a magnetar. Now, take everything we know about neutron stars, the density, the gravity, the compactness, and add a magnetic field so intense that it can literally tear atoms apart, not just ionize them like regular radiation does, not just heat them up. It rips apart the structure of matter itself. A typical pulsar already has a magnetic field trillions of times stronger than Earth's, but magnetars crank that number up so high that it stops being relatable. The field of a magnetar can be over 1,000 trillion times stronger than Earth's. If you were anywhere near one, even thousands of kilometers away, your atoms would not hold together. The very chemistry of your body would fall apart under the magnetic pressure. And it is not just theoretical. We have observed their effects. In 2004, a magnetar named SGR 180620, located about 42,000 light-years away from Earth in the constellation Sagittarius, released a burst of gamma radiation so intense that it caused sensors on multiple satellites to overload, even though it came from the other side of the galaxy. For a fraction of a second, that magnetar outshone every other X-ray source in the sky combined. If it had been just 10 light-years closer, Earth would have been in serious trouble. Because unlike pulsars, which spin and fade gradually over time, magnetars are unstable. Their magnetic fields do not stay quiet. They build up tension beneath the crust, and sometimes the pressure becomes too much. This causes what is called a starquake. Imagine a planet-sized object made of ultra-dense neutron matter cracking open like an egg under too much pressure. The crust shifts, the magnetic field suddenly realigns, and the resulting release of energy is so massive that it makes our most powerful nuclear weapons look like firecrackers. These quakes unleash bursts of gamma and X-ray radiation that travel across space at the speed of light. And there is no warning, no build-up, just a sudden flash. The energy of 100,000 suns released in a fraction of a second. We are lucky, by the way. The closest known magnetar is about 8,000 light-years away. That is far enough that even a massive flare would not do much damage to Earth. But scientists have calculated that if one went off within about 40 light-years, it could strip away our ozone layer, exposing the planet to deadly ultraviolet radiation from the sun. And here is the kicker. Magnetars do not live long. Their intense magnetic fields decay quickly over just 10,000 to 100,000 years, which is a blink of an eye in cosmic terms. That makes them rare. For every 1,000 neutron stars, only about 10 are expected to be magnetars. But that is still enough. One is enough. The magnetic field is so powerful that even when the magnetar is quiet, it is still affecting its surroundings. Any nearby planets, assuming they even exist, would be constantly bathed in high-energy radiation. And if a flare did happen while a planet was close, the result would be instant sterilization. You do not need a supernova. You do not need a black hole. You just need a crack in the crust, and it is game over. That is what makes magneteers a different kind of danger. They do not announce themselves with pulses. They do not get louder over time. They are like cosmic mines, sitting in place, quiet, waiting. And if the conditions line up just right, they detonate. So, we have got neutron stars that spin fast enough to create artificial-looking beacons. We have got magnetars that hold the record for the strongest magnetic fields in the known universe. And we have got at least one pulsar in our own galaxy that is balancing on the edge of collapse. But let us ask the next logical question. What if one of them was closer? What if somehow one of these stars drifted into our neighborhood? So far, everything we have talked about has felt distant. 14,000 light years, 42,000 light years. Even the nearest magnetars are thousands of light years away, comfortably tucked away behind an ocean of space. And that is probably why most people do not feel the weight of it. Cosmic danger, when far enough away, does not feel real. But let us bring it closer. Let us say one of these neutron stars, does not matter if it is a pulsar, a black widow, or a full-blown magnetar, somehow got kicked in our direction. Maybe from a supernova explosion, maybe a gravitational nudge from another star. Space is chaotic, and neutron stars have been known to move. In fact, some of them are moving at speeds of over 1,500 kilometers per second, fast enough to leave the galaxy entirely. Now, imagine one of those stars, maybe even PSR J09520607 itself, somehow found itself within the orbit of Jupiter. Let us say it parked itself about 500 million miles from Earth. That is still far, right? Jupiter is out there. No big deal. Think again. First, the gravity. Even from that distance, the gravitational pull of a neutron star that massive would start disrupting the orbits of nearby planets. Jupiter, Saturn, and even Uranus might experience orbital shifts. Over time, their paths would destabilize, creating gravitational chaos that trickles inward toward Earth. Then comes the radiation. A pulsar like J09520607 does not just sit quietly. It emits twin beams of high-energy radiation from its magnetic poles, beams made of X-rays, gamma rays, and charged particles. If Earth happened to be in the path of even one of those beams, we would be in serious trouble. Our magnetic field would offer some protection for a while, but the intensity would eventually overwhelm it. The ozone layer would be the first to go. Without it, solar ultraviolet radiation would begin sterilizing the surface, and it would not stop there. The constant exposure to high-energy particles would start breaking molecular bonds in the atmosphere. Satellites would malfunction. GPS would be lost. Radio communications would collapse. The night sky would be flooded with unnatural light. And the auroras, those dancing green lights near the poles, would spread across the entire planet, flickering non-stop like a warning. And if it is a magnetar instead of a pulsar, well, the rules change. A magnetar does not need to spin at 700 times per second to cause chaos. All it needs is proximity. If it were within just a few thousand kilometers, the sheer strength of its magnetic field would start pulling at the electrons in the atoms that make up your body. You would not even see it coming. Your body's structure would simply dissolve. Not from heat, not from radiation, just raw magnetic force. And even if you were watching from a distance, say from the moon, the view would not be much better. Earth would start to deform. not all at once, but slowly. Tides would go wild, the crust might shift, volcanoes would awaken from dormancy as the pressure underneath builds. Earthquakes would ripple through continents as the gravitational stresses mount. Eventually, the atmosphere itself could be stripped away, blown into space by radiation pressure and magnetic interference. The oceans would boil, then evaporate. The surface would be scorched. Life would vanish, not in centuries or decades, but in hours. And yet, for the neutron star, none of this would be noticeable. To a pulsar or a magnetar, Earth is just another rock, a piece of space debris that happened to get too close. Our sun is barely a snack. If the neutron star had enough mass, or if it kept pulling matter in through an accretion disk, it could eventually collapse into a black hole right there in our solar system. At that point, gravity would dominate completely. Planetary orbits would collapse inward. The sun itself would spiral toward the event horizon and vanish. And that would be the end of the story. Now, obviously, the odds of this happening are extremely low. Neutron stars are fast and powerful, but space is vast. Most of them are traveling through the galaxy in isolation. And even though a few 100 million exist in the Milky Way, the chances of one wandering into our backyard are lower than winning the lottery every day for the next century. But that is not really the point. The point is, these objects exist. They are real, and they are not rare. They are scattered all across the galaxy, some spinning faster than any human-made machine, some glowing with invisible beams of deadly radiation, some with magnetic fields strong enough to destroy planets without ever touching them. And some of them somehow have planets of their own. After everything we have said about neutron stars, the gravity, the radiation, the magnetic fields that could tear atoms apart, it would be fair to assume that nothing could survive near them. Certainly not something as fragile as a planet, and yet a few have. Not many. In fact, only about 0.5% of all known pulsars have been found to host planets. That is out of the thousands we have detected. But those rare exceptions raise a strange question. How can a planetary system survive around one of the most violent objects in the galaxy? Let us start with the basics. Most stars form planets from leftover material, the gas and dust swirling around them during their early life. But pulsars are formed in the exact opposite way, from destruction. A massive supernova explosion wipes everything out, and what is left behind is a crushed core spinning like a blender with a magnetic field that could sterilize entire solar systems. So, the original planets are gone, which means that if a pulsar has planets, they either formed after the supernova or they were somehow captured later. One of the most well-known examples is PSR B WOW 57+12, located about 2,300 light-years away. It was the first pulsar ever found to host planets. And believe it or not, it was also the first confirmed discovery of any exoplanets at all, back in 1992. This pulsar has 3 known planets, all of them rocky, all of them bigger than Earth. And what is strange is that they orbit in relatively stable paths. Not normal circular orbits like we see in our solar system, but highly elliptical, meaning they swing close and then far away as they loop around. The gravitational environment around a pulsar is so intense that even small deviations become amplified. So the fact that these planets are still there and still orbiting is weird. Now imagine living on one. This would not be like Earth. The skies would not have sunlight or a blue atmosphere, they would be black, permanently. Your sky would flash regularly with bursts of radiation, depending on whether the pulsar's beam crossed your location. Instead of sunlight warming the planet, you would get occasional pulses of high-energy particles, enough to sterilize any exposed surface. The only chance for life to exist would be deep underground, shielded by miles of rock, maybe under thick ice, maybe in subsurface oceans. Some scientists think these planets might have formed from supernova debris, material that did not escape into space, but fell back inward and eventually cooled into a dusty disk. Over millions of years, that material could have clumped together into rocky worlds. Others think the planets might be fragments, pieces of a companion star that was shredded by the pulsar's gravity, like cosmic leftovers compressed into orbit. There is also the possibility that these planets were captured, rogue planets drifting through space, caught by the pulsar's intense gravitational pull. This is less likely, but not impossible, especially if the pulsar once had a companion star that got ripped apart and left behind planetary debris. Regardless of how they formed, these planets are survivors. They have withstood radiation, magnetic storms, and gravitational chaos, and they still orbit quietly around one of the most dangerous objects in existence. Another pulsar, PSR J2007+3120, has at least 2 known planets. Again, both several times more massive than Earth. One completes an orbit every 1.9 years. The other takes 3.6 years. And just like with BWOW57+12, their paths are not smooth or gentle. They are elongated, chaotic, and constantly shifting, like a car trying to drive in a hurricane. The weirdest part is that we do not know how rare this really is. We have only detected pulsar planets around a handful of neutron stars, but that might just be because they are hard to see. After all, we are trying to spot tiny worlds orbiting objects that are barely the size of a city across thousands of light years of space. And yet, they are out there. If life ever did evolve on one of these worlds, it would have to be unlike anything we can imagine. It would not just have to survive harsh conditions. It would have to be built for radiation, for chaos, for sudden bursts of energy that could melt an atmosphere in minutes. Which brings us back to Earth. We orbit a calm, steady yellow star. We have a mild magnetic field, a breathable atmosphere, liquid water on the surface. In every possible way, our solar system is unusually quiet. The fact that neutron stars can even have planets just makes it clearer how strange and lucky our situation really is. But let us circle back now, because this whole story started with a title, The Most Dangerous Stars in the Universe. And the question is simple. Should we be worried? We have talked about stars that spin faster than jet engines, crush matter tighter than atomic nuclei, and shoot beams of radiation that could melt the surface of a planet. We have looked at pulsars that are eating their companions alive, and magnetars that could crack open like lightning-filled eggs and blast radiation across light years. It sounds like a horror movie, but here is the truth. No, we do not need to worry. Not in the way people usually think about danger. PSR J0952 is not about to collapse into a black hole tomorrow and erase us from existence. Magnetars are not hovering nearby, ready to fry our atmosphere. These things are real, but they are also far. That is what saves us. Space, as it turns out, is still very, very big. The most dangerous stars in our galaxy might explode, yes, But any minute in cosmic terms could mean tens of thousands of years or longer. And if something like that did happen, the radiation would take just as long to reach us. So, even if the collapse already happened, we would not know. We would be staring into the past, like we always are when we look at stars. But that does not mean these things are irrelevant. Pulsars, neutron stars, and magnetars are not just freak objects floating in the void. They are reminders that the universe does not run on comfort. It runs on physics, on pressure and collapse, on spin and radiation, on gravity pulling things inward until they cannot hold their shape anymore. These stars show us what happens when things are pushed to their absolute limit and beyond. They tell a story that is less about threat and more about scale. Because what we call normal, a calm star, a stable orbit, an atmosphere that protects us, that is the exception. Most of the universe is rough, unforgiving, full of energy being released in ways we can barely understand, by objects we would never survive being near. So no, we are not in immediate danger, but yes, we should pay attention. Because somewhere not that far from here, a star is spinning itself apart, gaining mass, losing stability, getting closer to the edge. And when it goes, it will not leave a warning. And if you are someone who finds comfort in the stars, remember that not all of them are friendly. Some of them are just waiting to collapse. That is the quiet horror of the cosmos. It is not that these monsters are coming for us. It is that they are out there at all, doing what they do, indifferent to everything we call home. And the only reason we are safe is that we happen to be in the right place at the right time, living on a quiet little planet, orbiting a quiet little star, in a quiet little corner of a galaxy that is, at this very moment, full of stars that are anything but quiet. In the deep black of space, somewhere beyond the dust and darkness of the galactic plane, a star burns so wide that light itself takes most of a working day just to cross from one side to the other. If you dropped our entire solar system next to it, the star would swallow every planet, every asteroid, every comet, and still have room left over. The star we are talking about is a red hypergiant, a celestial monster that pushes against the very laws of physics. But before we meet that beast, we need to understand why such giants exist at all, how they hold themselves together, and why nearly everything we think we know about stellar size comes with a giant question mark attached. This is the story of the biggest star in the universe. Not just one star, but the search for the ultimate champion, the current record holder, the theoretical limits that prevent stars from growing even larger, and the ghosts of giants that may have already exploded before humans ever looked at the sky. Let us begin with a simple fact. When you step outside on a clear afternoon and look up at that blazing yellow disk, you are staring at a star, our star. For most of human history, we assumed it was the center of everything, the biggest, brightest thing in existence. And then we learned how wrong we were. Our sun is about 865,000 miles across. You could line up 109 Earths across its face. You could pack more than 1 million Earths inside it. Those numbers feel impossibly huge until you realize that in the family of stars, the sun is small, almost forgettable. It is an average yellow dwarf, nothing special. Now imagine every grain of sand on every beach on Earth represents a star. Our sun would be one of the smaller grains, lost in a desert of giants. Some grains in that desert are the size of basketballs, some the size of buildings, a few the size of entire cities. Astronomers measure stars using something called solar radii. One solar radius equals the distance from the sun's core to its surface. So when scientists say a star is 1,000 solar radii wide, they mean its diameter is 1,000 times that of our sun. The numbers we are about to explore reach into the thousands, some past 2,000. That means you could drop our sun next to these giants and it would become invisible, a pinhead next a basketball. But here is the first big insight. The size of a star is intimately tied to its color. And color is not about motion, it is about temperature. A red star is cool, around 3,000 degrees Fahrenheit at its surface. A yellow star, like our sun, is warmer, about 10,000 degrees. White stars are hotter still. Blue stars are the elite, burning at 20,000 degrees and beyond. Blue giants are the stars that carve out the most extreme lives, but red supergiants and hypergiants are the ones that swell to ridiculous dimensions. Why does color matter? Because the temperature determines how much energy the star radiates per unit area. A cooler surface means the star must be enormous to produce the blinding amount of light we see from across hundreds or thousands of light years. That is how we spot these monsters. They are stupidly bright, yet they look red. The only way that works is if they are huge. So how do we even measure something that appears as just a point of light in even the most powerful telescopes? Astronomers use a clever trick. First, they figure out the distance using parallax, the apparent shift of a nearby star against distant background stars as Earth moves around the sun. Once the distance is known, they measure the star's apparent brightness and its color. From the color, they get the surface temperature. Then they apply a law of physics called the Stefan-Boltzmann law, which relates how much energy a glowing object emits to its size and temperature. If you know how bright the star truly is and how hot its surface is, you can solve for its radius. It is a beautiful piece of mathematics that turns a single point of light into a cosmic ruler. But there is a catch. The most enormous stars are often shrouded in the material they themselves have ejected, cloaked in dust and gas that can distort the measurements. Some stars change size dramatically as they pulse, and the light from the most distant giants takes thousands or tens of thousands of years to reach us. So when we look at these monsters, we are looking at a snapshot from the past, and some of those snapshots are already lies. The stars that sent them might already be dead. We might be observing ghosts. Let us take a tour of those giants, starting with a star that taught astronomers a hard lesson about brightness and distance. Look up at the winter night sky and find Sirius, the dog star, the brightest star visible from Earth. The ancient Egyptians built calendars around it. Polynesian sailors navigated by it. For centuries, astronomers assumed Sirius must be a giant because it outshone everything else. They were tricked. Sirius is only 8.6 light years away, making it one of our closest stellar neighbors. Its brightness comes from proximity, not size. In reality, Sirius measures just 1.7 times wider than our sun. A modest jump, hardly a giant at all. The night sky lies to us. A flashlight held close looks brighter than a stadium spotlight a mile away. Sirius was the master illusionist that fooled astronomers for generations. But Sirius also had a secret. In the 1840s, astronomer Friedrich Bessel noticed it wobbling slightly as it moved through space. Something invisible was tugging on it. He predicted a hidden companion. Years later, telescopes caught a faint glimmer beside the bright star. They named it Sirius B, and Sirius B turned out to be a corpse, the burnt-out core of a once mighty star, now compressed into an object the size of Earth, but holding nearly the mass of our Sun. A teaspoon of its material would weigh several tons. That was the first confirmed white dwarf, and it taught astronomers something profound. To find the true giants of the universe, you cannot trust your eyes. The real monsters often hide farther away, dimmer to our view, but bigger than anything close by could dream of being. So, astronomers started hunting deeper. Their first major prize was in the constellation Orion, at the Hunter's Foot, a point of cold blue-white light called Rigel. Rigel sits about 860 light-years away. Its light left that star around the time medieval knights were riding through Europe. And despite that vast distance, it still ranks as one of the brightest stars in our night sky. A star that bright, that far away, has to be a beast. Rigel measures about 78 times wider than our Sun. If you swapped our Sun for Rigel, the inner planets would be incinerated instantly. Mercury, Venus, and Earth would be inside the star. And Rigel pumps out 120,000 times more energy than our Sun every second. That blue color is the giveaway. Blue stars burn at over 20,000 degrees Fahrenheit. They burn through their fuel at a terrifying pace. While our Sun has happily burned for 4.5 billion years and has another 5 billion ahead, Rigel is only about 8 million years old and will explode as a supernova within a few million years, a heartbeat in cosmic time. When it goes, it will outshine every star in the night sky combined. People on Earth, if humans still exist, will see a second sun appear at night. But as impressive as Rigel is, it is just a teenager among supergiants. The real monsters are the red ones. Turn back to Orion's shoulder. That deep orange-red ember is Betelgeuse. Betelgeuse is a red supergiant about 640 light-years away. It measures somewhere between 700 and 900 times wider than our Sun, depending on when you measure it, because the star pulses. Drop it into our solar system, and it would swallow Mercury, Venus, Earth, Mars, and the entire asteroid belt. Its outer atmosphere would brush against Jupiter's orbit. Our planet would not just burn, it would be inside the star. Betelgeuse is not stable. Its surface boils with convection cells larger than the orbit of Mars. The whole star breathes like a living thing. In late 2019 and early 2020, Betelgeuse dimmed dramatically. People wondered whether the star was about to explode. Astronomers discovered that the star had ejected an enormous cloud of dust that blocked some of its light. The dimming was a warning. Stars this big do not behave nicely as they approach death. They convulse, they throw off material, they flicker. Betelgeuse will explode as a supernova sometime in the next 100,000 years. Possibly tonight, possibly tomorrow, possibly 50,000 years from now. When it does, the show will be unforgettable. It will become brighter than the full moon, visible during the day. At night, it will cast shadows. And because the light takes 640 years to reach us, the explosion may have already happened. The signal might be racing toward us right now. Moving south toward the constellation Scorpius, we find another red supergiant with a name that means rival of Mars. Antares. Antares lies about 550 light-years from Earth. Its diameter stretches about 700 times that of our Sun. If placed where our Sun sits, its outer edge would extend past Mars and reach almost to Jupiter. Earth would be vaporized in a flash. Antares burns at a cooler temperature, around 6,000 degrees Fahrenheit, which is why it looks red. Despite the cooler surface, it puts out nearly 70,000 times the energy of our Sun because of sheer size. Antares is dying, fusing heavier elements in its core. It is currently cooking carbon, oxygen, and neon. Each new fuel buys less time. The carbon stage might last 1,000 years. The neon stage might last a year. The final stages take days. When Antares finally explodes, the supernova will briefly outshine the full moon. But Antares is not the largest red supergiant, not even close. There are stars that make it look like a candle. Deeper in the northern sky, in the constellation Cepheus, sits a star so red that the great astronomer William Herschel nicknamed it the Garnet Star in the 1700s. Its formal name is Mu Cephei. It is about 20,500 light-years away. Its light has been traveling since the time of ancient Greece. Estimates of its size vary, but it is roughly 1,400 times wider than our Sun. Drop it into our solar system, and it would swallow everything out to the orbit of Saturn. Earth, Mars, Jupiter, all gone. Mu Cephei pulses irregularly, its brightness changing over cycles of 2 to 12 years. It also leaks material constantly, forming a faint luminous fog around itself. Mu Cephei emits about 350,000 times the light of our Sun, most of it in infrared. If our eyes could see infrared, it would dominate a large patch of the night sky. Then there is VV Cephei, a star that breaks what we think of as normal celestial mechanics. VV Cephei A is a red hypergiant about 5,000 light-years away. It measures between 1,000 and 1,600 times wider than our Sun. That range exists because the star is so chaotic. If it replaced our Sun, its outer atmosphere would extend past Saturn. But here is the strange part. VA has a companion star, VB, which is itself massive, about 10 times wider than our Sun and burning blue hot. The smaller star actually skims through the outer layers of the bigger star during part of its orbit. It plows through the giant's puffed-up gaseous envelope every 20 years, stirring up massive amounts of material, creating shock waves and bizarre brightness changes. Nothing about this setup is stable. Eventually, the gravitational chaos will rip the system apart or merge the two stars. These monsters are so loosely held together that their average density is incredibly low. In the outer layers, the gas is thinner than the air inside a vacuum chamber on Earth. Most of the mass is concentrated deep in the core. So how do these stars hold themselves together? They hold together through a delicate balance between gravity pulling inward and radiation pressure pushing outward. In the core, nuclear fusion produces a flood of energy. That energy, in the form of photons, slams into atoms and pushes them away from the center. For most stars, gravity easily wins and the star stays compact. But for these hypergiants, the radiation from the core is so powerful that it almost overcomes gravity. The star skirts the edge of a physical boundary called the Eddington limit. Beyond that limit, the outward push would blow the star's outer layers completely away. These giants survive because they are constantly shedding mass, bleeding material into space in a slow, controlled disintegration. Strong magnetic fields may also help contain the outward pressure. though astronomers are still figuring out the details. One hypergiant that pushed astronomers to the edge of their equations is KY Cygni, in the constellation Cygnus. It sits about 5,000 light-years away. Early measurements put it at nearly 2,050 solar radii, which would have made it one of the biggest stars ever discovered. But that number broke the models. If KY Cygni were that large, it would violate the Eddington limit. So astronomers rechecked the data, accounting for dust that affects brightness readings. Newer estimates brought it down to about 1,030 to 1,400 solar radii. Still a monster, but no longer a paradox. The story of KY Cygni reveals how messy the leaderboard is. Measurements depend on dust, distance, brightness assumptions, and which model of stellar physics you use. A star that looks like a champion one year might be downgraded the next. Another extreme giant hides at the edge of our galaxy, about 9,000 light-years away. It is called V354 Cephei. It measures between 600 and 890 solar radii, depending on the measurement. At its largest, it would extend past Jupiter's orbit. What makes V354 Cephei interesting is its location on the outer fringes of the Milky Way, far from the crowded core where most massive stars are born. How did a monster get so big out there? Possibly it drifted outward over millions of years, or it is the lone survivor of a cluster of massive stars that has since dispersed. Whatever its origin, V354 Cephei is in the late stages of its life, fusing heavier elements and throwing off material that will seed future stars and planets. Now, we travel to a truly bizarre star cluster about 12,000 light-years away in the constellation Ara. It is called Westerlund 1, and it is a stellar nursery on steroids. Inside this cluster, dozens of massive stars are crammed into a tiny pocket of space. The undisputed king of Westerlund 1 is Westerlund 1 to 26, a red supergiant possibly verging on hypergiant status. Size estimates range from 2,000 to 2,500 solar radii. If correct, that places it firmly among the largest stars ever measured. Drop it into our solar system, and its outer edge would extend past Saturn, possibly toward Uranus. Westerlund 1 to 26 sits dangerously close to the Eddington limit, possibly even crossing it. How does it hold together? Strong magnetic fields may wrap around the giant like invisible webs, and the star is likely losing material fast enough to prevent immediate destruction. Westerlund 1 to 26 is also surrounded by a huge shell of radio-emitting material, one of the brightest natural radio sources in our part of the galaxy. The entire cluster is only about 4 to 5 million years old, a baby in stellar terms, yet the star has already aged into a red supergiant. It will not last much longer. Within the next few 100,000 years, it will explode. Leaving our galaxy entirely, we travel about 160,000 light-years to the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. Inside it lurks one of the most extreme stars ever discovered, WOH G64. It is a red hypergiant with a diameter estimated at around 1,540 solar radii. But what makes it truly bizarre is what surrounds it. The star is wrapped in a thick, dense torus of dust, a donut-shaped cloud of material that the star itself has been throwing off for hundreds of thousands of years. The torus is so thick that it obscures most of the star's light from our perspective. Looking at WOH G64 is like trying to see a light bulb through a wool blanket. The dust shell stretches for about 120 trillion miles and contains material equivalent to several times the mass of our Sun. WOHG 64 is shedding mass at one of the highest rates ever recorded, losing a sun's worth of material every 10,000 years. It is essentially eating itself from the outside in. Closer to home, but even stranger, is the star RW Cephei in the constellation Cepheus. RW Cephei is a yellow hypergiant, though its color shifts unpredictably. It lies about 3,500 light-years away. Its size varies wildly, from 900 to 1,600 solar radii, because the star physically swells and shrinks. RW Cephei is in a transitional phase of its life, caught between being a red supergiant and a stripped-down Wolf-Rayet star. It is not even spherical. Recent observations suggest it has bulges and dimples on its surface, huge convection cells that make it look lumpy like a glowing apple beginning to wrinkle. It throws off material in bursts rather than steadily. In recent years, it dimmed significantly due to a major dust ejection event, similar to what Betelgeuse did. Another hidden giant is NML Cygni, about 5,300 light-years away. It measures between 1,100 and 1,600 solar radii. It is so dim from Earth because it is wrapped in an enormous shell of dust that absorbs almost all of its visible light. Through infrared telescopes, it lights up like a beacon. NML Cygni is losing mass at a furious rate, throwing off an Earth-sized chunk of matter every few months. Each pulse of the star causes another round of mass ejection, feeding the dust shell that surrounds it. In the constellation Sagittarius, near the heart of our galaxy, sits VX Sagittarii, a red hypergiant about 1,520 light-years away. It measures around 1,520 solar radii at its peak. It is bleeding into space at a rate of roughly 1 Earth mass every couple of months. The star is in a real sense evaporating, with material gushing out in every direction, creating a thick glowing envelope that telescopes can resolve as a fuzzy halo. VX Sagittarii pulses irregularly, its brightness changing over cycles of a couple of years. During bright phases, it becomes visible to the naked eye from the southern hemisphere. During dim phases, it requires a telescope. The material being shed by VX Sagittarii contains heavy elements forged in its core: carbon, oxygen, silicon, iron, which will become part of the next generation of stars. Without giants like this, there would be no carbon for life, no oxygen for water, no silicon for rocky planets. For many years, one star dominated the leaderboard of cosmic giants, Vi Canis Majoris. It sits in the constellation Canis Major, about 3,900 light-years from Earth. In its glory days, Vi Canis Majoris was estimated at around 2,000 solar radii. More recent measurements have brought that figure down to about 1,300 to 1,700 solar radii, still enormous, no longer the champion. Its outer atmosphere is so loosely bound that material peels away constantly, forming an extensive nebula of ejected gas and dust. Photographs from the Hubble Space Telescope reveal chaotic swirling clouds that look more like an explosion frozen in time than a steady stellar wind. The cause may be massive convection cells, each one the size of our entire solar system, bursting at the surface and launching colossal amounts of material into space. Vi Canis Majoris is also dimming slowly over time as the growing dust cloud blocks more light. We are watching the star disappear behind its own breath. But the current heavyweight champion, the star that now holds the title of biggest known, is Stephenson 218, often shortened to ST218. It sits about 20,000 light-years from Earth in the constellation Scutum, inside a star cluster called Stephenson 2. Estimates place Stephenson 218 at around 2,150 solar radii. That is the most reliable current figure. At that size, the star would dwarf our entire solar system. If placed where our Sun sits, its outer atmosphere would stretch far past the orbit of Saturn, possibly out toward Uranus. Light takes about 9 hours to cross its diameter. That is longer than a workday. Light from our own Sun makes the same journey in about 2 seconds. The star is a red supergiant, possibly a red hypergiant. Its surface temperature is around 6,300 degrees Fahrenheit, cool enough to explain its deep red color. Despite that cool surface, it pumps out energy equivalent to about 440,000 times that of our Sun, almost all of it in infrared. The cluster around it is itself a cosmic oddity, a group of about 24 red supergiants all packed together, a remnant of a massive star-forming event about 20 million years ago. Most of those stars are already dead.